Morning, everybody. Can you listen to me? Please raise your hand. As I told, from today onwards, we will go up to 1 o'clock, sir. In few days, we can really complete the syllabus. That will boost a lot of confidence. And this is already November now. Today is November 1st. Okay, then you'll have ample time for revision. Okay, so that is my plan here. We will go ahead aggressively today up to 1 o'clock. Okay, what do you say? Is it okay? Raise your hand again. Yes, very good. So, see, I know, sir, this online teaching is a different methodology, even for us, now, sir. Like we have to adapt. There is no other way now. So listen carefully, whether you are listening in a mobile phone or laptop or computer, desktop, please listen carefully. Keep writing whatever minimum you can whenever a problem is asked. And then, however, we are sharing the videos and also the notes, okay, na? Classroom notes. So don't worry. At the end, when I complete the syllabus in few more days, then I will give whatever you want, okay, extra books, complete PDF file, etc., etc. Okay, na? Yes, now let us continue. But what we did yesterday, quick review. Quick review what we did yesterday. See, yesterday we were continuing doing problems in AC steady state, but see this problem which came in gate. But I modified all bits for the given waveform. Average value is the DC component. RMS when both frequencies are different is like Fourier series. That is a C bit I did first. Then B bit. RMS when both frequencies are same is not Fourier series. Then add the phasors. Okay, after adding the phasors, we got the expression. Okay, then we got the RMS. Then this is case one, sinusoidal supply to linear load. Okay, because it is an RC load, RC nature. Okay, now because reactance is negative. Then this is case two, non-sinusoidal supply to linear load, because this is Fourier series expanded. When two sources at different frequency means it is coming from Fourier series concept, please. So here there is no single impedance angle or single phase angle. We have to do the power triangle way. So first average power we got, okay, and then power factor by calculating both P and S. Then we came to case three, sinusoidal supply to non-linear load. This is power electronics. From that, all these things, okay, we got. Okay, but here total power factor is fundamental power factor into distortion factor. Okay, this fundamental power factor is called displacement factor. This is called current distortion factor. Then average value, okay. Then circuit theory, we started slowly finding power factor, impedance reduction, started the transformation, short circuit definition. Thevenin's category 3, we already did Thevenin's category by Ohm's law. Okay, then passive reduction. Okay, then we came to voltage division rule, but these notations are important, sir. The values you write by taking maximum value as reference. I'm sorry, the values you write by taking maximum values as reference is called phasor value. Otherwise represent as a function, but the best way is RMS value or working value. Then current division rule, here directly polar quantities RMS value or working value. Okay, na? Working value means RMS value. Okay. Then one calculation problem completely we did, sir. All things we calculated. Okay. Also check these formulas. Okay, and then we did draw the phasor diagram. This was very interesting conclusion about phasor diagram. Okay, now then after that, mesh analysis, nodal analysis, theorems we started, source transformation technique. Then we did one problem where we did by superposition, Thevenin's and also Norton's. Okay, now chalo. So we'll continue from there. Everybody, let us continue from there. Okay, so let us continue from there, everybody. Is a gate 2 marks question, everybody, quickly and determine current I in the circuit. Current I in the circuit shown. Determine current I in the circuit shown. This voltage is 40 sine 2t volts, 10 volts, 2 ohms, 1 ohm, 2 Henry, 1 Henry, 1 by 6 farad. And he's asking this current I. Chalo, quickly observe, I'm doing the problem now. Straight away, I'm doing the problem. Determine current I in the circuit shown. Okay, determine current I in the circuit shown. Determine current I in the circuit shown. Okay, chalo, now listen, I'm going with solution. Listen now. See here, yes, here there is both AC signal and DC signal. Okay, it is a mixed mode problem. So we know steady state AC circuit analysis and also we know steady state DC circuit. Okay, this is a mixed mode. Okay, mixed signal analysis. And we know inductors, capacitors are frequency dependent components. Now for DC signal in steady state, yes, for DC signal in steady state, you know, inductor short, capacitor open. And for AC sinusoidal signal in steady state, inductor is a lagging element, capacitor is leading element. So how can we do both together? Here we need to use superposition theorem. So use superposition theorem as network is excited. Network is excited. Okay, with multiple frequency sources. Multiple frequency sources. That is important. As a network is excited with multiple frequency sources. So now in that regard, everybody, now in that regard. Step 1, I will take AC source only. Shall I will take AC source only. Shall if I take sinusoidal source only, okay, inductor lagging element reactance. Now this DC voltage source shorted. Okay, I will show like this. Okay, now this is, you know, this voltage is how much? 40 sine 2t volt. Now because here omega is 2, okay, first of all resistor is same. This DC voltage source I shorted. Now for omega equal to 2, this become plus J4 ohm, this become minus J3 ohm, and this become plus J2 ohm. And let this current be I dash. Okay, na? So for this signal where omega is 2, this is plus J omega L, this is minus J by omega C, like that. Now I dash. Now current division rule I will do. This I dash is first of all total voltage by total impedance seen by the source. Total voltage by total impedance is how much? This 1 plus J4 minus J3. See, don't forget this minus J3 in the bottom. These three become series now, sir. 1 plus J4 minus J3 is 1 plus J1. 1 plus J1 plus these two in parallel. 2 in parallel to J2. Yes, 2 in parallel to J2 is total voltage by total impedance. Total current we get into current division rule. I need this branch current now. This branch current is total current into opposite 2 by sum 2 plus J2. 2 plus J2. Now if you solve this carefully now, sir, with calculator, you will get a current something like 10 sine 2t minus 90 amperes. 10 sine 2t minus 90 amperes. Okay, na? Chalo, I'm going to step 2 now. Yes, I'm going to step 2. Now, if I go to step 2, DC source only. DC source only. Okay. If I go to DC source only, everybody. So now what I will do, AC voltage source ideally 0 impedance shorted. Okay. Now for DC inductor short, this inductor is also short, capacitor is open, and this resistors however will work. This is for DC source only. This is DC steady state. This is however 1 ohm. This is 2 ohms. This is 10 volts. Okay, this inductor is shorted, and capacitor is open, sir. And let this current be I double dash. Now current cannot flow here, so I double dash is 10 by 2, 5 ampere, same direction. So now I will say by superposition theorem, this total current I is I double dash plus I dash. I double dash is 5. Where is I dash? Chalo, I dash is 10 sine 2t minus 90. 10 sine 2t minus 90. This is the answer. Option in gate. Okay, na? So here, because there are two sources at different frequency, one is ideal DC 0 frequency, ideal AC omega equal to 2. So circuit will behave in different way as components behave in different way, especially inductor, capacitor, frequency dependent components. So that is why I need to apply which theorem here? Superposition. And moreover, to find I dash, I took directly the functions, are no confusion. Don't worry here, RMSA bags. I directly took the function. So directly function you take, the magnitude will be divided by 4, you will get 10, and phase shift at the bottom will be 45, you take up minus 45, so 90. You'll get this current as lagging. You do it, sir. This calculation part, of course, you have to do it, sir. Please understand. Okay. This entire calculation part, I request you to do. Take time, sir. Learn, but learn. Okay, na? Chalo, now I'm going to next problem here. This again gate bit. Gate 2 marks 2018. Okay, I want everyone to do this. Find Thevenin's voltage. Thevenin's voltage across the load. Find Thevenin's voltage across the load. Okay. Yes, I want everyone to find this. Find Thevenin's voltage across the load. Angle 53.12 volts. This is 3 ohms, J 4 ohms, VL J 8 ohms, 6 ohms, RL equal to 10 ohms. If that is VL, NVL, and if this is current I, yes, if this is current I, this is J40 I volt. So there are dependent sources. Determine the Thevenin's voltage across the load. Okay, this is 3. I am writing again. So determine the Thevenin's voltage across the load. So where is the load here? Everybody, where is the load here? Everybody, load is here where 10 ohms is connected. Load is here where 10 ohms is connected. Okay, determine the Thevenin's voltage across the load. Determine the Thevenin's voltage across the load. So load is here. Okay, na? Yes, load is here. So quickly, sir, 2 minutes I'm giving, right fast. Okay, sure, I'm doing the problem now. See, determine the Thevenin's voltage. See, luckily in this problem, he's asking only Thevenin's voltage, sir. If the question is about Thevenin's equivalent, then it is a tough problem because it is Thevenin's category 2, where there is an independent AC voltage source and a dependent AC sources. If it was equivalent, I told now, sir, if it was equivalent, then VOC by ISC you have to do, and then ZTH will come, and then equivalent. But luckily here is asking only Thevenin's voltage, only one step. So that is why in AC steady state we will never ask big problems. So only Thevenin's voltage. Chalo, sir, we know Thevenin's voltage is the open circuit voltage. Yes or no? Yes, Thevenin's voltage is the open circuit voltage. Everybody observe now. So the moment, now see the same problem if I want to find the Thevenin's voltage, which is the open circuit voltage. So these are my target terminals AB. Okay. Now I will remove this. Yes, Thevenin's voltage is what? Open circuit voltage. Okay. This itself is Thevenin's voltage between AB across the load. See, the moment I make this, what are the changes? First of all, I become 0. So first of all, here observation, I becomes 0 because open circuit now current cannot flow. So there is no voltage drop across these passive elements. Then automatically you observe, VTH is nothing but 10 VL. Yes or no? VTH is 10 VL. We need VL. But the moment I is 0, listen now, the moment I is 0, okay, this dependent voltage source also becomes 0. The moment I is 0, this is J40I na, the dependent voltage source also becomes 0. The dependent voltage source 0 can be replaced by short circuit. The dependent voltage source becoming 0 can be replaced by short circuit. Sure, now sir, simple. If you can find VL, VTH, just tell VL. Now what is VL? Voltage division rule. This VL is total voltage into, okay, same by sum. Okay, this if you do, this you will do, you will get 80 at an angle 90 volts. Now then I will say this VTH is 10 VL. That is 10 into VL is 80 at an angle 90. So finally VTH is 800 at an angle 90 volt. But this 90 I can show with J operator, na sir. J 800 volts. Because I told J means 1 angle 90, like that. J means 1 angle 90. Okay, that is the meaning. Okay, so observe, sir, what are the changes? See later in what you say, in correlation to this what I'm sharing, the notes also I will share, so then you can see all these questions also again. Don't worry. See Thevenin's voltage across the road. This is a gate bit, however, you will find in our gate material also. So Thevenin's voltage is the open circuit voltage. The moment I open, what are the changes? First of all, current is 0. Current is 0, then dependent voltage source in the left side also becomes 0. Dependent voltage source 0, shorted. Then VTH is 10 VL. Okay, then VL I got by voltage division, and 10 into VL is VTH. Okay, now that is a very simple problem. Yes, some students are already right. Yes, some students are already giving answers. Very good, sir. Very good. Okay, now very good. So now let us go further. Now, sir, see, we covered Thevenin's category 2, Thevenin's category 1, and also Thevenin's category 3 yesterday itself in impedance. Like that, I am doing all the models here. Okay. Now we are coming to theorem 5. Theorem 5. This is very special theorem. That is maximum power transfer theorem in AC networks. Okay, maximum power transfer theorem in AC networks. Okay, na? Now this is very special. Let us see why. Okay, now listen carefully. Though there are 3 types of physical concepts. Okay, physical power concepts. Okay, power concepts in AC networks. That is real power, reactive power, apparent power. Okay, na? But the power, okay, but the power that is convertible or utilizable, the power that is convertible or utilizable in any form is active power or real power P in watts. In watts. See, this is very, very important statement. Why this is only important? Though there are three types of physical powers in AC networks like real power, reactive power, apparent power, but the power that is convertible or utilizable in any form is active power or real power P in watts. Okay, now that is the reason. Okay, so maximum power, okay, transfer. So maximum power transfer in AC networks, okay, then maximum power transfer in AC networks is confined to real power P only, and that too in the resistive part of the load network, resistive part of the load network. So please understand this statement. Everybody read 1 minute. I'm giving you time. Just read. Everybody read. See, though there are three types of physical powers in AC networks, but the power that is convertible or utilizable in any form is active power only. Yes, the power that is convertible or utilizable in any form is active power only, real power only. Okay. So maximum power transfer theorem is confined to which power? Active power only, and that too in which part? Resistive part of the load network. Okay, that too in the resistive part of the load network. Okay, now that is what you have to understand. Resistive part of the load network. Okay, now in this, let us consider first a general case. Now, what is general case? In general case, here we are assuming that both load resistance and reactance is adjustable. Now, this is a practical AC voltage source. Okay, practical AC voltage source is sinusoidal voltage generator in series with source impedance. The source impedance has source resistance and also source reactance. Okay, this is having source impedance and source reactance, and load is also impedance. Okay, which is having load resistance and load reactance. So here total impedance variable means, please understand the meaning. Here total impedance variable means load resistance as well as load reactance are independently controllable. That is the meaning. Here total impedance variable means, yes, load resistance as well as load reactance are independently controllable. That is the real meaning of this. Okay, now. So first we are talking general case. What is general case? In general case, source has impedance, load has impedance. Everybody, okay? In general case, source has impedance, load has impedance. But we are able to adjust only the load side. Now in the load side, total impedance variable means resistance and reactance both are independently controlled. Now here don't misunderstand, this excess is inductive, sir. This excess could be inductive or capacitive. Okay, now that you remember. Excess could be inductive or capacitive. If it is inductive, then plus JXL will come. If it is capacitive, minus JXC will come. Similarly, load reactance, I am never saying it is inductive by default. If it is inductive, again plus JXL will come. If it is capacitive, minus JXC will come. Okay, so that is the meaning here. That is the real meaning here. Okay, now. So in general case, total impedance variable. Yes, in general case, total impedance variable means, yes, load resistance and load reactance are independently controllable. So in general case, total impedance variable means load resistance and load reactance are independently controllable. Okay, now that is very expensive. In fact, resistance, how can you vary, sir? Connect heater, geyser, incandescent bulb, iron box, because these are resistive loads. But varying reactance is not a joke, sir. It is expensive. Okay, now. So now in that regard, everybody, now in that regard, yes. Now here both load side, okay, load side resistance as well as reactance can be independently controlled. Okay, here both load resistance and load reactance can be independently controlled. Okay, so we can compensate. Okay, we can compensate Okay, the net reactance, okay, net reactance to 0, because both load resistance and reactance is controlled now, sir. We can compensate the net reactance to 0. How to compensate net reactance? Suppose source side large inductor, connect capacitor, then XL minus XC should become 0. Or if source side there is capacitor, put inductor, then again we can compensate. So we can compensate the net reactance to 0, and circuit operates. Yes, circuit operates, okay, operates at unity power factor, okay, that is purely resistive. Okay, so here I use the term, so here both, so I will use this very interesting term given in textbooks. So here both phase balancing, not even phase balancing, I will explain, sir. Here both phase balancing, okay, so here both phase balancing and magnitude balancing, okay, balancing, okay, of impedance can be achieved, here both phase balancing and magnitude balancing of impedance can be achieved. Okay, so Pmax, I will tell you the meaning, sir. So Pmax occurs in the load, if okay, load impedance is, if load impedance is complex conjugate of source impedance. I will tell you the meaning. Okay, chalo, everyone should listen. See, what is this general case, everybody? See, general case is a case where load side I am able to independently control resistance as well as reactance. That is called general case. And this is not easy because resistance varying is okay, sir, because we can put heater, incandescent bulb, iron box, etc. But reactance varying is not a joke. You need to connect inductor bank, capacitor bank, and that too compensating equal to source is very expensive thing. But in general case, we are able to do that, both load resistance and reactance we are able to control. That is the first thing. Okay, na? And that is the first thing. Circuit operates at unity power factor. Why? Because if source is inductive, put capacitor. If source is capacitor, put inductor. Okay, like that. So now for what value of XL net reactance is 0? For what value of XL net reactance is 0? Yes, when XL is, see, for what value of XL net reactance is 0? When XL is minus XS, na? That is the meaning. XL is minus XS. Then only net reactance 0. See, when net reactance is 0, okay, circuit is purely resistive, unity power factor. At the same time, once net reactance is 0, now what, for what value of RL Pmax occurs in RL? We know this, na, sir. For what value of RL Pmax occurs in RL? When RL is RS. When RL is RS. Now this number is what to this number? You see now, load we are adjusting like this, then only Pmax occurs in the resistance. Finally, our target is what's our load resistance. See, finally our target is this load resistance. Okay, power. So first of all, compensate reactance, that is XL is minus XS. Okay, now first of all, XL is minus XS. And also what you do, yes, and also what you do, RL should be RS. First of all, XL is minus XS and RL is RS. Okay, if you do that, yes, if you do that, you will get it. Okay, if you do that, you will get it. That is the real meaning. Okay, now if you do that, you will get it. Okay. So now in that regard, yes, now in that regard, this is what to this number, this is what to this number. Yes, this is ZL is ZS star. Na, this is complex conjugate. Na, that is the reason I told this. Now you see here compensating both reactances is possible. Net reactance is 0 and Pmax occurs when load impedance is complex conjugate of source impedance. Then what is this statement, everybody? Here phase balancing and magnitude balance. What does it mean? See, now if you see here, if I write the magnitude of this is root of RS square plus XS square, and angle is what? Tan inverse XS by RS. Okay, and there also what is magnitude? Root of RS square plus XS square, and what is the angle? Minus tan inverse XS by RS. Now, if you see the magnitudes are equal, na? And also if you add the phase angles, combine the impedance, net phase angle becomes zero. Na? See the concept, sir. First of all, load impedance is complex conjugate of source impedance. That is why here I will write a statement that ZL is ZS star. That is a very important concept. ZL is ZS star. Okay. Then that is why this we got. And now if you convert into polar form, this is a magnitude and phase angle, magnitude and phase angle. See, magnitudes are equal to root of R square. So that is why balancing magnitude. And if you add the total impedance, the net phase angle becomes zero because resistance net phase because plus tan inverse excess by R and here minus tan inverse excess by R net phase. So that is why phase balancing and magnitude of balancing of impedance can be achieved and Pmax occurs when load impedance is complex conjugate of source impedance. Okay, that is the reason. Okay, that is why all this explanation I wrote there. Then in that regard, so now under this case, net reactance is zero. Now total resistance is how much? Total resistance is nothing but yes, Vs by 2 Rs it will be because Vs by this net reactance zero, Vs by Rs plus Rs, 2 Rs. Then power will be how much? That current square into R. So then load current will be what? Vs by 2 Rs. Then what is power maximum? Power maximum, this IL square into R L or RS only will come na. RL is RS only na. So that is nothing but Vs square by 4 RS square into RS because RL is RS. So finally this P max value is also Vs square by 4 RS watts. But this Vs is what value? RMS value. Okay, RMS value. Now think about what to do with any circuit. Okay, this I gave here example by taking a practical voltage source. But think about what to do with any circuit. I'm giving you 1 minute. Think Okay, understood now, sir. This is general case. So general case is where both are independently controlled, phase balancing and magnitude. Phase, because if you add the impedance, net phase angle 0 and impedance magnitudes are equal. That is the meaning. Okay, now. So this formula looks like this: V S square by. Now in general, for any circuit, what we have to do then? For any circuit, what we have to do then? Yes. Now Thevenin's. For any circuit in general, okay. First use Thevenin's theorem. Okay. First use Thevenin's theorem. Yes, Thevenin's theorem. Okay, now first use Thevenin's theorem. Okay. So what I will do? Suppose any complex network came. Yes, any complex network came. You want to maximize power in the load, which is load resistance and load reactance. Okay, I want to maximize by varying total resistance. Total impedance is total resistance as well as total reactance. Now what you do? First convert into Thevenin's equivalent. Yes, Thevenin's equivalent. Once you get converted into Thevenin's equivalent, okay. First, once you convert into Thevenin's equivalent, then I can say, then for P max, then for P in the load, okay, ZL is ZS star. ZL is ZS star. But here we have to write ZTH star. Yes or no? That is the same meaning. You write here ZTH star. That is the difference. And also this P max value now will be, instead of source, it will be Thevenin's voltage. VTH square by. Okay. So first of all, ZL is ZTH star. Yes, ZL is ZTH star. Okay. And also P max is VTH square by 4RH. Okay. ZL is ZTH star. And P max is VTH square by 4RH. Okay. So now once we concluded, that is general case, and for any network, first use Thevenin's theorem, and we can again conclude. Same meaning now, sir. ZL is ZS star, but here ZL will be ZTH star. Okay, this ZL means this load impedance only. Here also I will write small l to understand. Okay, no, that is the meaning. Okay, load impedance. Okay, no? Okay, and then this is what same meaning will come. Okay, no? But remember Thevenin's RMS voltage here. Now I am coming to special case A. What is the special case A? Special case A, again I am taking sinusoidal AC voltage source. Sinusoidal AC voltage source in series with impedance. Again here source impedance has source resistance and source reactance. Okay. Yes. Again I am taking sinusoidal voltage source in series with impedance, source resistance and source reactance. Again, don't misunderstand, it is inductive. It could be inductive or capacitive, but load is purely resistive. Load is purely resistive. This is what is the meaning of special case A. So in special case A, again it is a practical AC voltage source which consists of voltage source in series with impedance. Okay, that could be inductive or capacitive. This excess is called source reactance. I'm never arguing inductive or capacitive. It could be inductive or capacitive, but load is purely resistive. Now, which loads in electrical engineering? Which loads in electrical engineering are purely resistive? Which loads in electrical engineering are purely resistive, sir? Like iron box, incandescent bulb, heaters, like that. Okay, that is the meaning there. That is the meaning. Okay, now here, load is purely resistive. Load is purely resistive. Okay, load is purely resistive. Okay, but source has impedance. Okay, now source has impedance. Okay, source has impedance. So here, okay, phase balancing of impedance is not possible. I will tell you the meaning. Phase balancing of impedance is not possible. That means net phase angle will never become zero, na? Like in the previous case, you see you add the phase angle plus tan inverse xs by r, and here also rs, of course, here it is understood xs by rs, here also xs by rs. Okay, na? So if you add the net, zero will come. Okay. But here, if you observe in this case, you will never get that. The net phase angle cannot become zero because one is resistive, one is impedance. So yes, phase balancing of impedance is not possible. So at least match the magnitudes only, magnitudes only. Okay. So I will write. So that is the meaning. What is the meaning? See, suppose if you write this, first if you write the impedance here, root of rs square plus xs square, and this is what angle plus tan inverse xs by rs. Okay, but here if you go, magnitude is r, angle is 0, magnitude is rl, angle is 0. So phase balancing is not possible. Now, sir, if you add the phase angle, they are not 0. So at least match the magnitude. So that is why. So P max occurs in the load. So P max occurs in the load. P max occurs in the load. Okay, so P max occurs in the load if RL, yes, P max occurs in the load if RL is modulus of ZS, that is nothing but root of RS square plus XS square. Okay, that is magnitude balancing only. That is magnitude balancing only we are doing. Okay, but remember here we cannot use any formula. But to find this P max value, PL max value or P max value. Okay, but to find this P max value, yes, but to find this P max value, but to find this P max value, resubstitute this calculated RL back into the circuit, yes, back into the circuit, and find RMS current through it, and then power, But to find this Pmax value, resubstitute, yes, but to find this Pmax value, resubstitute this calculated RL back into the circuit and find RMS current. That means don't use any formula like previous case. In previous case, we use this formula, sir, Vs square by 4RS, here not possible. So first, only magnitude balancing, that is RL equal to modulus of ZS. This is the condition for Pmax. Okay, now after that, what you do, then substitute this RL back into the circuit and find current and then power. Okay, that is the meaning that you have to understand. Okay, that is why here I wrote important point. Here, phase balancing of impedance not possible. So at least match the magnitude. That is the meaning. So if you add these impedances, phase angle never cancels, but magnitude only at least match. That is the argument. That is special case A. Very interesting. Okay, now I'm coming to special case B. Special case B. Very interesting, sir. Very, very important this theorem. In this AC steady state, this is a very special theorem. Okay. Now, what is special case B? Here also I am taking practical AC voltage source. Practical AC voltage source consists of sinusoidal voltage generator in series with impedance. Yes, sinusoidal voltage generator in series with impedance. That is having source resistance and source reactance. It could be inductive or capacitive. Here, interestingly, load is also impedance. Here, interestingly, load is also impedance. Here, interestingly, load is also impedance. Load resistance and load reactance. Okay, load resistance and load reactance. Okay, here interestingly, load is also impedance. That is load resistance and load reactance. Okay, load resistance and load reactance. Okay, but only resistance is adjustable. Only resistance is adjustable. Only resistance is adjustable. Resistance is adjustable. Okay, now that is the meaning. Only resistance is adjustable. Okay, that is very interesting. In general case, both are adjustable now, but here only resistance is adjustable. So here also reactance is fixed now, sir. Reactance is fixed means we cannot compensate reactance. So again here phase balancing of impedance is not possible. So only match the magnitude. But in matching the magnitude for resistance, you should include in the load side reactance. Okay. Now listen to this what I am writing. So yes, here though both source and load. Both source and load have impedances. Here both source and load have impedances. Only load resistance is adjustable. Here, though both source and load have impedances, only load resistance is adjustable. Okay, so we cannot, okay, we cannot compensate. We cannot compensate the net reactance. The net reactance to zero. We cannot compensate the net reactance to zero. So here also, phase balancing of impedance is not possible. Okay. Here also, phase balancing of impedance is not possible. So at least match the magnitude. The magnitudes. Okay, at least match the magnitudes. Okay, but we should include even the load side reactance. So this case and this case is almost same, sir. This case and this case almost same. Where here also only resistance variable, here also only resistance variable. But extra is this reactance partner. So Pmax occurs. So I will write Pmax occurs in the load. Pmax occurs in the load. If this RL is magnitude of the rest of the impedance. What is the rest of the impedance here? Force side as well as load side reactance. That is nothing but RS plus JXS plus JXL. Again, everybody, this could be inductive or capacitive. Please understand, this could be either inductive or even capacitive. Don't misunderstand that I am putting plus here. You can take plus if it is inductive, if it is minus, take. That could be anything, sir. That is why don't misunderstand. XS is called source reactance, XL is called load reactance. But I am never mentioning whether it is inductive or capacitive. Okay, na? So that is nothing but RS plus J into XS source reactance, XL load reactance. So finally, this RL is magnitude na. So root of RS square plus XS plus XL square. That is the answer. Okay, na? Please understand this. Okay, read this again. I will explain. Read this. Yes, please. Really sorry. Like my stomach was upset, sir. Really sorry. Can you listen to me? Please raise your hand. Everybody, please excuse me. See, actually my stomach got upset, sir. I went for washroom. Really sorry. Okay. One request: whenever you start speaking, please open video. Okay, open video because sometime our earphones not working properly. Okay, I will do that. Okay, that is not an issue. That I will do that so that you can see. I understood. Yes. Okay. Chalo. Now see, sir. Everybody, see the reason I took break because I was really my stomach was upset. Okay, chalo. Now listen, everyone. See in special case B, here also source is impedance, load is impedance. Source is impedance, load is impedance, but only load side resistance is adjustable. Okay, only load side resistance is adjustable. Okay, na? Yes. Load side resistance is adjustable. Okay. Now, when it is only load side resistance adjustable, please understand when it is only load side resistance adjustable, here again phase balancing is not possible because reactances are fixed now. We cannot compensate reactance, only magnitude. But in equating the magnitude, we should conclude or including the load side reactance. That is the requirement. Okay, that is the requirement. Okay, that you please understand here. Okay, na? That is very interesting here. Then I'm going to special case C. Now this is special case C. See, even doubts I will take up at the last. Okay, na? Special case C. Special case C. Okay, na? Now what is the special case C here? Source is impedance. Yeah, practical voltage source in series with impedance. Practical voltage source in series with impedance. This is source resistance and source reactance. Okay, source resistance and source reactance. Okay. Load side. Also load resistance and load reactance. Okay. This is source resistance and source reactance. This is load resistance and load reactance. Okay. But here only reactance is adjustable. Here only reactance is adjustable. Okay. Here only reactance is adjustable. That is the first thing. So here only reactance is adjustable. Okay. Now here we can compensate the net reactance to 0. Yes. So here since only load reactance is adjustable. Okay. We can compensate, okay, the net reactance to 0. Net reactance to 0. Okay. So here phase balancing is possible. Phase balancing of impedance is possible. Impedance. Okay. Impedance. Okay. Can be achieved. Okay, achieved. But magnitudes are fixed. Why magnitudes are fixed? As RL is constant. As RL is fixed. We cannot adjust RL mass, that is fixed. So the only way is to compensate the reactance. So what is the only way to compensate reactance? XL is minus XS. So Pmax occurs. So Pmax occurs in the load. So Pmax occurs in the load. Load if X reactance, we have to compensate only the reactance. So Pmax occurs in the load if XL is minus XS. XL is minus XS. That implies XL plus XS is 0. XL plus XS is 0. Okay, XL plus XS is 0. Okay, yes. Pmax occurs, yes, if XL is XS is 0. Okay, that is a big thing. That is a big thing here. Okay, yes, that is the reason. Okay, so this is so understand all the cases. See, first general cases, both are impedances and both load side resistance and load side reactance are adjustable. Okay, then special case A, Load is only resistance and that is adjustable. Here phase balancing not possible, magnitude equal. Special case B, both are impedance but only resistance is adjustable. Again, phase balancing not possible, only magnitude, but we have to include the load side reactance. Then both special case C, both are impedance but only reactance is adjustable. So we can compensate the net reactance to zero. Yes, we can compensate the net reactance to zero. Okay, but resistance is fixed. So that means here phase balancing is possible, but magnitudes are fixed like that. All cases we wrote, sir. That is very, very interesting and important. All cases we wrote. Okay, now, now, sir, now I will ask some bits here. Okay, think and tell. I will ask some bits. Now, first in general case, yes, in general case, okay, what is the power factor and efficiency? Everybody watch this. So in general case, I'm asking, in general case, what is the power factor and efficiency? Okay, now, what is the power factor and efficiency? Very simple. See, in general case, you know, net reactance zero, na sir, net reactance zero. Okay, so unity power factor na purely resistive. So power factor is one, and efficiency is how much? When RL is RS, 50% efficiency. 50% efficiency. We learned like that, na? Yes, that is important. Okay, so power factor is one, efficiency is 50%. That you remember, this bit came in IES. So in general case, power factor is one because net reactance zero and efficiency is 50%. Okay, na? So now when it comes to special case A, now here what is this? Power factor is less than one. Power factor is less than one, and efficiency can be anything, sir. Efficiency can be anything. Efficiency can be anything. Okay, that can be anything. Power factor is less than one and efficiency can be anything. Okay, power factor is less than one and efficiency can be anything. Okay, power factor is less than one, efficiency is any percent. Okay, power factor is less than one, efficiency is anything. Okay, that's the reason. And when it comes to special case B, okay, when it comes to special case B, okay, when it comes to special case B, yes, when it comes to special case B, yes, everybody please understand when it comes to special case B, yes, here again you see reactance exists. So power factor is again less than one. Again, efficiency can be anything. Percentage efficiency can be anything. Okay, it can be anything. Anything from 0 to 100. Okay, then when it comes to special case C, here net reactance 0. Here power factor is 1 because net reactance is 0. But again, efficiency can be anything. Efficiency eta can be anything. Efficiency eta can be anything. So that is it. Okay. Now I'm asking a gate question. So everybody should answer this gate question. Okay, gate question. Now interesting question, sir. Everyone, interesting question. Gate. Everyone, listen to this question. Okay. For what value of source impedance? For what value of source impedance ZS? Pmax occurs in the load. For what value of source impedance ZS, Pmax occurs in the load? Okay, look at this question. For what value of source impedance ZS, Pmax occurs in the load? Think and answer. For what value of source impedance ZS, Pmax occurs in the load? Here we are adjusting the source. Here we are adjusting the source for maximize power in the load. So first of all, here also P max, which power? Real power. Na? Here also we are adjusting real power. Na? Real power means first of all compensate the reactance. So first is XS should be minus XL. And then what about RS? RS should be 0. Source side, na sir, minimum resistance will give, then P max. Then P max occurs in this resistance. So first of all, compensate reactance. So final answer is yes. Final answer. Okay, I will write that side. Yes, I write here. Final answer is yes. Please understand. Final answer is ZS is minus JXL. Okay, ZS is minus JXL. Okay, ZS is minus JX. Okay, that is the reason. Okay, that is the answer. Okay, so now I am coming to general question. Okay, yes. What is the maximum power? Okay, what is the maximum power transferred? What is the maximum power transferred to the load? This is 40 sine 2t volt, 2 ohm, 1 Henry, half farad, 1 ohm, and this is 5 cos 2t minus 30 degree. Okay, so what is the maximum power transfer to the load? So everybody see this, everybody do this now. What is the maximum power transfer to the load? Okay, chalo, this comes under general case or special case ABC na. See, this comes under general case. Why? Because load is totally varying, na sir. See, the meaning of this question is what is the maximum power transfer to the load? So what is the maximum power transfer to the load means? Yes, total impedance is variable. So this comes under, this is general case. Okay, na? General case. Why general case? Because here total impedance is variable. total impedance variable means it is understood that resistance and reactance is variable. Now that is coming under general case. Okay, na? Yes, that is coming under general case. Okay, now in this general case, yes, everybody. Now in this general case, okay. Now we know Pmax occurs if ZL is ZS star, but source is a complex system. So Thevenin, so we know that Pmax occurs if ZL is ZTH star. That means indirectly Thevenin is required na. Chalo. Now first of all here, this I will write it as 40 angle 0 volts. Okay. This I will write it as 5 at an angle plus 60. See, one is sine, one is cos. Observe, cos theta is sine 90 plus theta. When both are given, you have to do the phase shift I told. So one is sine, one is cos. Yes, cos sine 90 plus theta. 90 minus 30, 60. I know this 40 is maximum value. Here 5 is also maximum value. I know this 40 is maximum value and 5 is maximum value, please. Okay, na? Yes. Now for omega equal to 2, chalo, for omega equal to, this becomes how much? Plus J2 ohm, this become minus J1 ohm. Now I am finding the Thevenin. Now I am finding the Thevenin. Now I am finding the Thevenin. Okay, now I am finding the Thevenin equivalent. Okay, now Thevenin equivalent. So first step, I'll find ZTH. Yes, voltage source short. Current source is open. Two ohm, J2 ohm, minus J1 ohm, 1 ohm. This is ZTH. Okay, this ZTH is how much? Two plus J2 ohm. This ZTH is 2 plus J2 ohm. Okay, na? ZTH is 2 plus J2. Okay, so ZTH is really 2 plus J2. Okay, na? Yes, 2 plus J2 ohm. That is very good. Then, because voltage source short, current source open. Then I want VTH. Okay, then I also want VTH. Open circuit voltage, because Thevenin is required indirectly here, sir. I know this side took as 40. I know 40 is maximum value, but let it be there, phasor value. And this current also 5 angle 60. I told why, because one is sine, one is cos. This is current, this is voltage. But now I need this Thevenin voltage. Now I need Thevenin voltage. Now, sir, for that I will write a simple KVL. Okay. See now, this current is always constant. Huh? This 5 amperes is going anti-clock. Okay. This 5 amperes is going this way, and this will be the voltage dropping. Then happily I will write a KVL. So if I write a KVL, minus of 40 angle 0 volts, minus of IZ. I is how much? 5 at an angle 60, because it is current source in series to everyone. Current is constant. Nah? Into impedance. What is impedance? 2 plus J2 plus VTH is 0. So this VTH will be how much now? VTH will be how much now? Yes, this VTH if you solve. Yes, this VTH if you solve, you will get this as 38.8 at an angle 20.6 volts you get. But this is what value? All 40 and 5 are maximum values now. So this is called phasor value. Phasor value. That is in terms of maximum I wrote. Okay, na? But RMS we will take for power calculation. Now Thevenin's equivalent is consisting of voltage source in series with impedance. Voltage source in series with impedance. Voltage source in series with impedance. Okay, that voltage is how much? 38.8. Okay, we converted both into sine as sine 2t. Okay, sine 2t, and it is coming as yeah plus 20.6 volts, and impedance is how much? 2 plus j2. Now I am connecting back the target and total load impedance variable. Chalo sir. Now because this 38.8 is phasor value or maximum value, I wrote the function here, no confusion. Now this is clearly maximum value. Now we can say, so now what is the conclusion for Pmax? For Pmax, one thing we can say, ZL is ZTH star. That implies ZL is, okay, ZL is ZTH star 2 minus J2. Okay, that is 2 minus J2. Okay, ZL is ZTH star, that is 2 minus J2 ohms. Okay, na? Yes, and ZL is ZTH star, and also, yes, and also I can say, yes, and also I can say, now for Pmax, yes, this Pmax value is how much? VTH square by 4 RTH. But that VTH is what? RMS value. RMS value. That is 38.8 by root 2 square, because root 2 is compulsory because this is maximum na, by 4 into RTH2. Okay, that you do, you will get 94.1 watt. Okay, go through this question, I will explain again. Chalo, go through this question. Imtiaz, Imtiaz, raise your hand. Imtiaz Pasha, raise your hand. Imtiaz, you wrote, oh, can we vary only RL to become RS inductive load? No. If load is purely inductive, where is the real power, sir? Okay, na? No, that is not the meaning. Okay. It is understood that in case A, that we are going to connect a reactance such that the net reactance of the source is compensated. That is the meaning. That is the meaning there. How 40 angle 0? There is a supply now. 40 is the maximum value given in the supply. This 40 angle 0. 40 is the maximum value. That is why I wrote here this 40 angle 0. Because it is having no phase shift of 40 sine 2t. So no phase shift, 40 angle 0, but 40 is maximum value. Here cos, so convert into sine. Sine 90 plus theta. 90 minus 30, 60. So 5 angle 60. 5 angle 60. Okay, that is the meaning. So now I'm coming to gate question, sir. Yes, now I'm coming to gate question. So this problem is a general case because total impedance variable. Total impedance variable means load resistance as well as reactance is adjustable. That is the reason we say total impedance. So here Thevenin's is indirectly required and we got this answer. Okay, now I am coming to gate question. Now this is a gate, wonderful gate question. Okay, everybody. What is the maximum power transferred to the load? What is the maximum power transferred to the load? What is the maximum power transfer to the load? So 2 minutes I'm giving, try everyone. I will give break at 9 o'clock. Quickly. What is the maximum power transfer to the load? Yes, everybody. Chalo, now see this. This is special case A because load is purely resistive. Na? Yes, this is special case A. This is special case A. Okay. This is special case A. Okay. So please understand. This is special case A. Okay. So please understand. This is special case A because load is purely resistive. Now here phase balancing is not possible, only magnitudes we have to balance. Okay. So here also Pmax occurs in the load when load resistance is magnitude of source impedance. But source is a big thing. So again Thevenin's required or not. So we use Thevenin's again. We use Thevenin's reductions first. Thevenin's theorem first. So here also we use what? Thevenin's. Here also we use Thevenin's. Okay na? Yes, here also we use Thevenin's theorem. Okay. So what is the required first Thevenin's impedance? Okay. Step 1, Thevenin's impedance. Now what is Thevenin's impedance? See, both are voltage sources this time. Short it. Here also short it. Both are voltage sources short. So this is 6 ohms, J8 ohms, J8 ohms, 6 ohms. And here I am going with Thevenin's impedance. So this Thevenin's impedance is clearly how much? 6 plus J8 is in parallel to 6 plus J8. So it is obviously 3 plus J4 ohms. So it is obviously 3 plus J4 ohms. Okay, na? So that is what, because both are parallel, both are voltage sources, are two impedances are equal in parallel. Z by 2 will be the answer. Okay, na? Like ZZ parallel becomes Z by 2. Then I want Thevenin's voltage. So now see the same problem. I am writing the Thevenin's equivalent. So for that I need Thevenin's voltage. This is 110 angle 0. And this is 90 angle 0. But remember now, here in this problem, this 110 and 90 are directly what values? RMS values. Na? In this problem, this 110 and 90 are directly what values? Yes, this 110 and 90 are directly RMS values because polar given now, directly RMS. Okay. This is however 6 plus J8. 6 ohms. Okay, now that is clearly this. Okay, 6 plus J8. That is clearly this 6 plus J8. Okay, now this is Thevenin's voltage. Okay, na? So directly nodal analysis I will do. Nodal analysis. So nodal analysis. So nodal analysis, that is VTH minus 110 by 6 plus J8 plus VTH minus 90 by 6 plus J8 equal to 0. Okay. Now if you do that, 2 VTH is 200. VTH is 100 volts. Okay, VTH is 100 volts. Okay, now Thevenin's equivalent. Now Thevenin's equivalent consists of voltage source in series with impedance. Thevenin's voltage, how much we got? 100 volts. That is our directly RMS. Thevenin's impedance is how much we got? Yes, Thevenin's impedance is 3 plus J4. So now I'm connecting purely resistance. Okay, I'm connecting purely resistance. So this is clearly special case. Yes, this is clearly special case. Yes, special case A. Yes or no? This is clearly special case A. So now for Pmax, we can now answer for Pmax. So here RL should be modulus of this impedance. Okay, 3 plus J4. That is 5 ohms. Yes or no? Then to find Pmax, no formula directly. Then first IL. IL is how much? 100 by total 3 plus J4 plus again 5 will come out. We calculated that. Okay, that will be given 11.18 angle minus 26.56 amperes. Now once we get this, then Pmax is IL square into R. $625 watts. Look at the conclusions. So here also this is special case A. Here see this special case A where load is purely resistive. So Pmax occurs in the load when load resistance is magnitude of source impedance, but source is a complex thing. So first we reduce into Thevenin's. Yes or no? After reducing in Thevenin's, then that is 5 ohms. And once you put 5 ohms, find RMS current and power. Find RMS current and power. Okay, that is the meaning. Okay. Okay, we'll take a break, but yes, doubts I will take up at the last, sir. 500 watts, why it is mistake? Whoever got 500, what mistakes you are doing, you think. First of all, these are directly RMS values. So don't do by root 2 again. You will get mistake otherwise. I told the difference. See the previous problem, what is the difference? See the previous problem, these are functions. These are given functions. So this 40 and 5 are maximum values. So your root 2 is compulsory. That is why your root 2 compulsory and formula we can use. But for this special case, we cannot use that formula. Okay, we cannot use that formula VTH square by 4 RTH. No, don't do. That is also another mistake you do. No, you cannot do like that. Okay, na? And moreover, this is directly RMS values that are all important, sir. And this answer will be 625 watts. Okay, na? 625 watts will be the answer. Okay, so we'll take a break of half an hour. Come by 9:35. Okay, we'll continue there. Yes, everybody, are you available? Please raise your hand. Yes, sir. So last problem, you see that was a problem which was given in GATE 2006 for electrical, and it comes under special case B because load is purely resistive. Okay, na? Load is purely resistive, and hence we got this. Okay, na? So now in that regard, I am going to the next GATE problem. Yes, this is also GATE question. Everybody now watch this. What is the maximum power transferred to the load? Okay, what is the maximum power transferred to the load? T cos 2t volt, 4 ohm, 2 Henry, R half. And this is the load. Okay. What is the maximum power transferred to the load? So everybody see that what is the maximum power transferred to the load? Okay, what is the maximum power transfer to the load? Now look at this, sir. Look at this. Very interesting. Look at this. Everybody look at this. See here. Source is impedance, load is impedance. But only resistance is adjustable now. Why? Because for fixed frequency, see already for a given frequency, here frequency is how much? 2 now, omega 2. For fixed frequency, this is plus J4 and this is minus J1. Okay, for fixed frequency, already reactances are fixed. Only resistance is variable. So this comes under special case B. Special case B. Why special case B? Because source is impedance, load is impedance, but only resistance is adjustable. Nah. Because reactances are already fixed here. Because omega is fixed. Special case B. And moreover, remember this 30 is what value, sir? This 30 is what value? Maximum value here. Be careful. Okay, let him be given cos. See, if question is given in cos, right answer same. If sine also, but both are given, then do phase shift. Always remember that. See here, input function is cosine, no problem. Sine or cosine is a sinusoid only. But if both are given, then there is a mutual phase shift that we have to consider. Chalo, now, sir, in special case B, Pmax occurs in the load if R is equal to magnitude of the rest of the impedance, including the load reactance. So we know directly for Pmax, R should be modulus of rest of the impedance, including the load side reactance. What is the including the load side reactance? 4 plus J4 minus J1, that is 4 plus J3, that is 5 ohms. That is 5 ohms. That is 5 ohms. That is 5 ohms. Okay. Yes. R is 5 ohms. Okay, everybody. R is 5 ohms. Okay. So now once we know R is 5 ohms, then let us find the load current. We cannot use any formula here also, sir. Okay. So once R is 5 ohms, let us find the load current. Now load current, I need RMS now for power. Be careful. RMS. But this 30 is what value? Maximum value. This 30 is maximum. Now here by root 2 will come. By root 2. Okay, at an angle 0. Here angle doesn't matter. But total impedance. That is 4 plus J4. 4 plus J4 plus R is how much? 5. plus 5, and this is how much? Minus j1, minus j. Okay, this you solve. You will get this current as some 2.236 at an angle minus 18.14. Now P max is this IL magnitude square into R. Okay, that is 2.236 square into 5. That is 25 watts. Wonderful gate question. Okay, one. But understand this is special case. Yes, special case B. Now I am giving an IES objective. Chalo, IES objective, everybody. Without calculator, you should tell what is the maximum power transferred to the load. What is the maximum power transferred to the load? Hundred volts, 10 ohms, J 10 ohms, 10 ohms. And this is the load reactance. Okay, load reactance. And this is the total load. Please tell you. Okay, what is the maximum power transfer to the load? What is the maximum power transfer to the load? What is the maximum power transfer to the load? What is the maximum power transfer to the load? Okay, now see here, everybody. This is clearly which case, sir? See, source is impedance, load is impedance. Yeah, this is source is impedance, load is impedance. Yes, source is impedance, load is impedance, but only load reactance is adjustable. So this is special case C. Special case C. Okay, this is source is impedance and load is impedance. Yes, source is impedance, load is impedance. Okay, this is special case C. Okay, source is impedance, load is impedance, and this is special case C. Okay, please observe this. Source is impedance and load is impedance, and this is coming under special case C. Okay, special case C. Okay, source is impedance, load is impedance, and this is special case C. So we know directly, now directly for P max, first of all, XL is minus XS, that is XL will be minus J10, that is a condition. Now again, what is the RMS current, IL RMS? Now here this 100 is RMS or maximum? RMS only, na? That is 100 by total 10 plus J10 plus 10 minus J10. That is 100 by 25 amperes. 100 by 20 is 5 amperes. Okay, na? This is 100 by 25 amperes. Now P max is this IL RMS square into R. Into that R of the load. This is nothing but, yes, this is 5 square RMS current into 10. That is 250 watt. 250 watt. So observe, sir, this is special case C directly. Okay, special case C. Now I'll give two special problems here. Watch all my models, sir, and you need not refer any textbook. I'm telling you. You watch all my models. You need not refer any textbook. I'm challenging you that. Okay, watch all my models. You will never require any textbook. See, we should not take that VTX square by 4 RTH because it is only valid only in general case. You see the reduction which I told you. I told already how to recognize RMS or maximum. I told 100 times. The last class only I told you. Please go to the previous class. You cannot ask like this now. 100 times I told. Function is given. It is called amplitude. Directly polar is given is RMS. You don't listen and again I ask. It is your mistake, please. Okay. Then here, this is directly 250 watt. Now see, this is special gate question given for electrical 2 marks. For what value of capacitor C, okay, for what value of capacitor C, maximum power is transferred to entire load. Okay, for what value of capacitor C, maximum power is transferred to the entire load. For what value of capacitor C, maximum power is transferred to the entire load. Okay, please understand this. For what value of capacitor C, maximum power is transferred to the entire load. Okay. For what value of capacitor C, maximum power is transferred to the entire load. For what value of capacitor C, maximum power is transferred to the entire load. Supply is 10 cos 100t. Okay, 10 cos 100t, and this is 0.5 ohms. Load is a combination of RC parallel and then series to inductance. Okay, this is 10 cos 100t. Okay, for what value of capacitor C, maximum power is transferred to the entire load. Okay, na? Sir, listen. C you are varying means actually your frequency is fixed, so you are varying C means reactance is varied. Now it is simple problem, but is confusing you by putting inductor also in the load side. That is the only confusion is creating in your mind. But this C alone varied means C alone varied, but frequency is constant means reactance alone is varied. Na reactance alone varied means this is coming under general case or special case ABC. This is coming under special case C only, na sir. But the capacitor C should be such that the net reactance of the circuit should be 0. So C should be such that capacitor C should be, C value should be such that I will write like this. Okay. C capacitor C value should be such that the net circuit reactance must be zero. Okay, and the C value should be such that the net circuit reactance must be zero. Okay, so for that, first I'm finding the total circuit impedance. First, let us find the total impedance. Now, if you find the total impedance, this Z will be, okay. Now, first of all, here you see this omega is 100 now. So, omega is 100. This become how much? Plus J. Omega is 100 into 5 milli. That is 1 by 2, J by 2. And this becomes how much? Minus J by omega C, like that. So, now if I do that, yes, this is J by 2 plus J by 2. Okay. So, now if you do that, total impedance will be, this is J by 2 plus 1 in parallel to minus J by omega C. That is the meaning. This is J by 2 plus 1 in parallel to minus J by omega C. That is J by 2 plus this into this by this plus this. So this will be now J by 2 plus, okay, this is minus J by omega C by omega C. If you take omega C minus J, this if you read, okay, this if you read, okay, rationalize this. That is J by 2 plus J by omega C minus J. I will rationalize by omega C plus J by omega C plus J. Now this Z will be, okay, this is J by 2. Now this is J square minus 1 minus J omega C by A plus B into A minus B, A square minus B square, A square minus B square. So that implies this Z is, okay, 1 by omega square C square plus 1 plus J into 1 by 2 minus omega C by omega square C square plus 1. Okay, this is the net reactance. So C should be such that the net reactance should be 0. I told C value should be such that the net circuit reactance should be 0. So now I will make the X net to be 0. If I make the X net to be 0, okay, that becomes what now? Half is equal to omega C by omega square C square plus 1. So omega square C square plus 1 is 2 omega C. Omega square C square minus 2 omega C plus 1 is 0. So omega C minus 1 whole square is 0. So omega C is 1. Omega C is 1. Finally, C is 1 by omega. That is, what is omega given here? Omega is how much? 100 na? Omega given is 100. So this is 1 by 100. So this is now 10 millifarad. Answer is 10 millifarad. Answer is 10 millifarad. Okay, answer is 10 millifarad. Yeah, answer is 10 millifarad. Meaning 10 millifarad. So another special problem. Everyone should answer this. Assuming both the source, voltage source, and the source and, okay, assuming both the sources, I will write like this. Assuming both the sources are in phase, yes, assuming both the sources are in phase, find the value. Chalo, find the value of R such that, okay, maximum power is transferred transferred from circuit A. Okay, circuit A to circuit B. Circuit A to circuit B. Okay, understand the question. Assuming both the sources are in phase. Okay, assuming both the sources are in phase, find the value of resistance R such that maximum power is transferred from circuit A to circuit B. Okay, circuit A to circuit. Okay, assuming both the sources are in phase, find the value of resistance R so that maximum power is transferred from circuit A. This is circuit A, this box, and this circuit B is this box. Okay, so find the value of resistance R such that maximum power is transferred from circuit A to circuit B. Okay, here both the sources are in phase. Chalo, such models we did in DC, sir. Chalo, do it fast. I am giving you 1 minute. See, assuming both sources in phase, everyone understand the question. Assuming both sources in phase means what is the meaning here? Yes, assuming both sources in phase means yes. That means if this is 10 angle 0, this is 3 angle 0, like that. Okay. If this is 10 angle 30, this is 3 angle 30. That is the meaning of assuming both sources in phase. Okay. Assuming both sources in phase means meaning is that. Okay. And for this condition, yes, assuming both sources in phase, what is the value of R for which Pmax? See, I told no, sir, whatever may be the complexity. Okay, whatever may be the complexity. See, under Pmax condition, the combined load impedance magnitude should be equal to source. Whether it is category 1, special case A, special case B, special case C, we are matching such that the phase balancing and magnitude balancing must be same. If phase balancing is not there, at least magnitude balancing. So it is true that whatever may be the circuit B, under Pmax condition, the combined load impedance magnitude should match with the A. Na? So under this condition, how much percentage of supply will drop here? If this is 10, yes, if this is 10, this drop will be how much? Yes, this drop will be how much? This drop will be, yes, 50, sorry, 5, yes or no? Because if really Pmax says the combined load impedance of circuit B should be equal to this. Phase balancing may or may not happen, but at least magnitude must be equal. So under this condition, 50% of supply should drop here. Supply is 10. So what is 50% of supply? 5 volts. That is the meaning. Supply is 10. What is the 50% of supply? 5 volts. Okay, that is the meaning of 5 volts. Okay, now I'll apply KCL here. Now if you apply KCL, incoming is equal to outgoing. So if you apply KCL here, yes, if you apply KCL here, incoming 10 minus 5 by 2 is equal to 5 minus 3 by R. 5 minus 3 by R. And he said both sources are in phase, so no confusion of phase shift also. So R equal to 4 by 5, which is 0.8 ohms. Think, sir, think. Doubts I will entertain at the last. Okay, now think. Take your time. There are so many ways to do it also, but the easiest shortcut way, fundamental way, I teach always in my class. Okay, if really Pmax occurs, the combined load impedance should be source. Under this condition, 50% drop will take place. So what is the 50% of supply? 5. So KCL you apply here. Incoming is equal to outgoing, we get the answer. Now to go further, I need concept of, okay, concept of complex power. Complex power. S star, VI star. Concept of complex power, S star or VI star. Concept of complex power, S star or VI star. Okay. Concept of complex power, S star, VI star. Okay, concept of complex power, S star, VI star. Okay, now what is this? Listen carefully. Complex power is a mathematical concept which will allow us to, okay, which will allow us to evaluate, okay, all the three physical types of power, all the three physical powers, P, Q, S, any element or network or system. Complex power is a mathematical concept which will allow us to evaluate all the three physical powers P, Q, S in any element or network or system, okay, directly by observing, directly by observing voltage and current phasors, but without declaring the network and its components. Okay. Complex power is a mathematical concept which will allow us to evaluate all the three physical powers P, Q, S in any element or network or system directly by observing the voltage and current phasors. Yes, directly by observing the voltage and current phasors, but without declaring the network and its components. Okay, but without declaring the network and its components. Okay, but without declaring the network. See the meaning, sir. See, already we know real power, reactive power, operant power. But what is this complex power? So it is only a mathematical way to find all these things if elements and network is not given. See, so far in all the problems, what happens are network he gave, element we know, what type of load, RL load, RC load, like that we know. But here, independent to any network or independent to any connection, if you don't know, still we can observe only voltage and current phasors to get the values. Okay, that is the reason. Now, here I star is complex conjugate of okay, here I star is complex conjugate of total current I. Here I star is complex conjugate of total current I, and the units of complex power, okay, and the units of complex power is also volt amperes. is also volt amperes. Vs. Okay, first of all, what is I star? Here, I star is complex conjugate of total current I, and the units of complex power is also volt amperes. Now, some students ask me, sir, why you take Vi star? What? Why not V star I? No. See, which is dynamic, which is static. Voltage is constant. Current keeps varying in our electrical system. Voltage is constant, but current keeps changing depending upon the nature of the load. Leading, lagging, current changes. So I star only we should take. Okay, na? Now understand this concept now. Okay, let us understand. Now the concept. Okay, I will give the concept here. Okay, listen carefully. Suppose there is a very complex load network. Now this is not a small element, sir. Let us say this is a very complex load network. Okay, load network. It is not a single element and we don't know the nature. But we are now able to observe only the current phasor and voltage phasor. We are able to now observe the current phasor and voltage phasors. Now let us say there is a complex load network and we are trying to observe yes, the only voltage now. See, if the network is declared like RLA, RCA, etc., we would have told directly, we would have taken real power as we did in the previous one. But here, understand that, yes, this network is not declared. Now, without declaring the network, like, distribution system. Now, imagine I am in a big colony called MIG colony in BHL. MIG colony has got total 3,000 houses. Okay, more than 3,000 houses. In 3,000 houses, how to calculate real power? Their reduction not possible, na, sir. Then we see the voltage and current phases of the system and we will tell. Okay, now to understand this, let us take a case. Okay, I am taking a case that, okay, consider an example case and we will assume, okay, assume lagging power factor load. Lagging power factor load. Just assume lagging power factor load. Okay, assume lagging power factor load. Let V is equal to V angle alpha. I is equal to I angle beta. Okay, V equal to V angle alpha, I equal to I angle beta. Okay, then what is S? S is V into I. S is V into I. Suppose if you take directly S is equal to V into I, then you see that will come as well. See, here we are assuming lagging power factor load. Lagging power factor load means current is lagging voltage. Yes or no? Current is lagging voltage. So with respect to voltage, current lags. Or I can say here alpha should be greater than beta. Now if you take S is V into I, if you take product, this is V, this is I, and product will give what? Alpha plus beta. Na? Product will give alpha plus beta. But this is clearly wrong phase angle. This is clearly wrong phase angle, wrong impedance angle. Better wrong impedance angle. Better I write like this. This is wrong power factor angle or phase angle or impedance angle. Okay, wrong power factor angle. Okay, wrong power factor angle. Power factor angle. Why? Let us take the phasor diagram and complete. Let us take the phasor diagram and complete. Okay, let us take the phasor diagram and complete. Okay. So now see, if I directly take VI product, see actually voltage phasor I know, current phasor I know, sir. This network I don't know. But to understand this concept, I'm assuming lagging load. First I'm assuming lagging load. Lagging load means what? Current is lagging voltage. Or with respect to voltage, current lags. So alpha should be greater than beta. But if you directly take the product, now, sir, everybody see here. If you directly take the product V into I, okay, if you directly take the product V into I, this comes something like Vi angle alpha plus beta, na? But this alpha plus beta together is a wrong power factor angle. Let us see why. Suppose if I take the phasor diagram, okay, if I take the phasor diagram, okay, with respect to some reference, with respect to some common reference, yes, with respect to some common reference, let us say V is already at V angle alpha. Let us say this is V and this is already alpha. Okay, V alpha. Okay, then I at angle beta. Where is I at an angle beta? This is I and this is beta. Okay, this is I at an angle beta. Okay, So this is V angle alpha, this is I angle beta. So what is the actual angle between them? The actual angle between them should be alpha minus beta. Na? This is the actual power factor angle. This is the actual power factor angle. Yes or no? Or actual phase angle between V and I. But directly if you take product, we are getting alpha plus beta, which is wrong power factor angle. So now what we do, we do the correction. So we do correction. The correction is, yes, the correction is, okay, the correction is, okay, the correction. What is the correction? S star you take. S star is what? V I star. So V is already V angle alpha. But what is I star? I star means conjugate. Na? What is I star? I star means conjugate. What is nothing but I angle minus beta. I angle minus beta. So now S star become, yes, V I, okay, angle alpha minus beta. This is the correct power factor. This is, yes, this is the correct power factor angle. Okay, this is the correct power factor. This is the correct power factor. Okay, this is the correct power factor angle. Okay, that is why that correction happens only if you take VI star, but not VI. Okay, now that is the first thing. Then what are its applications? What are its applications? Now I'm writing a note here. So see, first of all, complex power I will not use everywhere, sir. Okay, complex power I will use only when network is not declared and only voltage current phasors are given. Okay, now then I will get this. Now in verifying Theligun's theorem, yes, Theligun's theorem for AC circuits, yes, in verifying Theligun's theorem for AC circuits, and to derive the power flow equation in power system, okay, in verifying Theligun's theorem in AC circuits and to derive the power flow equation in power system, we should consider the complex power only, complex power S star only. Okay, so in verifying Theligun's theorem for AC circuits and to derive power flow equation in power system, yes, we should consider complex power S star only. Where we need to mathematically, okay, mathematically prove what? That is sigma Vk into Ik star is 0. This is the meaning here. Where K is the taking the value from 1 to B, where B is the number of branches in the network. What is B here? Yes, B is the number of branches in the network. Number of branches in the network. Where B is the number of branches in the network. Okay, that means what we have to prove. So that is nothing but, yes, sigma Vi star of default sources. What are default sources? Voltage currents. Okay, voltage currents is equal to sigma Vi star of sinks. Okay, of sinks. Okay, that sinks are RLC components. Okay, that is what we have to see. Sigma Vi star of default sources is sigma Vi star of sinks. Okay, that is what we have to prove. Okay, now I am giving two examples to verify this Theligun's theorem as well as this concept of complex power. So first gate question I'm giving. So first gate question I'm giving here. This is a gate question. Okay, if B is 7 plus J2 volts. Okay, if V is 7 plus J2 volts and I is 5 plus J5 amperes, determine PQS and total load network power factor. Total load network power factor. This is the load. Okay, and this is the I phasor he gave, and this is the V phasor he gave. Chalo sir, try everyone. If V is 7 plus J 2 volts, okay na, and I is 1 plus J 5 amperes, determine real power, reactive power, and apparent power, and also total load network power factor. Okay, total load network power factor. Chalo 1 minute, do it. Okay, everybody, see now. See, he gave voltage phasor and current phasor, but he did not declare network. Now we have to use complex power. That is what everyone should understand. Sir, why here only complex power is coming? Why we did not do in the previous problems means here network is not declared. Components are not declared. Only voltage and current phasors are given. Na? The solution is here we should directly consider S star. That is VI star. V is how much? 7 plus J2. I star is 1 minus J5. Okay, I star I wrote. So this is directly, yes, 17 minus J 33. 17 minus J 33. Okay, 17 minus J 33. Now P is how much? 17 watts. Okay, this QC is minus 33. So that is why it is capacity 33 watts. Okay, P is 17 watts, Q is 33 watts. Okay, QC, that is generating. Okay, then I can say this S star is root of P square plus QC square, root of 17 square plus 33 square, 37.1 VAs. Okay, that is 37.1 VAs. So we got real power. Yes, we got real power. We got reactive power. And we got even total power. Okay, we got even total. Okay, we got total power. Now power factor. So now if you do power factor is clearly P by S. Yes or no? Okay, power factor is clearly P by S. P by S. P is how much? 17. S is how much? 37.1. Yes or no? P is 17. S is 37.1. So it is 0.45. Leading or lagging? See, overall net reactance negative means it is capacitive. So it is leading. 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 Now, by mistake, you check. Suppose someone take directly VI answer, you get all wrong answers because you see the load. See clearly, you see load is current leading voltage. Na? You see the phase angle of current, tan inverse phi, phase angle of voltage, tan inverse 2 by 7. So tan inverse phi is greater than tan inverse 2 by 7. So clearly, current is leading voltage. So it is an RC network, and that secret will come only when I take what VI star, and then this is the answer. So overall RC, that is why leading power factor. Okay, now that is the reason it is a leading power factor. Okay. Now, sir, remaining topics of this chapter I am covering with a lot of gate bits. Okay. Now we are in a very comfortable stage in AC. Now this is a gate bit. If VR is 5 volts, okay, VC is 4 sine 2t volt, 4 sine 2t volts, then VL is dash, inductor voltage is dash. Two amperes. This is 1 farad. This is 5 ohms. Okay. And this is 2 Henry. 2 Henry. And he said VR is 5 volts. Okay. VC is this and is asking VL. So this is a question. It is a circuit part of a big network. VR is 5 volts. VC is 4 sine 2t. Then VL is how much? Chalo. Everybody, 1 minute, try something. everyone see, this is about KCL for any signal at any time. See, one is a DC signal, one is a sinusoidal signal, like that. So we are now applying KCL for any signal at any time. Okay, now listen carefully. Now he said VR is directly 5 volts. Okay, VR is directly how much? 5 volts. VC is how much? 4 sine 2t. Now for the given passive notation polarity, what should be this current and direction? Current should enter positive in a sync, na? And 5 by 5, this is 1 ampere. And what is this current? IC, this current IC will be IC dV by dt, na? That is nothing but C, yes, C dV by dt. d by dt of V of t, that is Vc of t, that is 4 sine 2t. Or you can do even phasor notation wise. That becomes now how much? 8 cos 2t. Because sine becomes cos, na? 8 cos 2t. Okay. Now I need VL. For that, let us find IL. Now for this passive notation inductor, current should enter positive, na? Current should enter. So this should be IL. So first, if you apply KCL, what is the KCL at this junction? What is the KCL at this junction? The incoming currents equal to outgoing. Incoming 1 plus 2 DC currents, outgoing. So this is KCL verification for any signal at a time. And outgoing currents are what? IL plus this is nothing but 8 cos 2t. Okay, this is 8 cos 2t. Okay, this is 8 cos 2t. Okay, now this is 8 cos 2t. Okay, na? So now IL is 3 minus 8 cos 2t. Then what is VL? Then what is VL? VL is L DIL by dt. L is how much we got? 2. He gave 2. D by dt of which current? D by dt of this current. So that is 2 into differentiation of constant is 0. Cos is minus sin plus 16 sine 2t. So overall VL is 32 sine 2t volts. 32 sine 2t volts. So look at this, sir. So we are applying now KCL for any signal at any time. Okay. So that is the meaning here. We applied KCL for any signal at any time. That is the meaning here. We applied KCL for any signal and any time. That is what we did here. Okay, na? That is the meaning here. Okay. So now I am giving another gate question given for instrumentation students. This is given for instrumentation students. Okay, na? Now write down this question here. The question is, yes, if IL of 0 means initial condition. Okay, if IL of 0, okay, IL of 0 is 1 ampere and IR of t is 4 e power minus 3t plus 3 e power minus 4t amperes for all t greater than or equal to 0. If IL of 0 is 1 ampere and IR of t is 4 e power minus 3t plus 3 e power minus 4t for all t greater than or equal to 0, find phase angle phi. Find phase angle phi. This is IL. Okay, and this is IR. This is 12 cos omega t plus phi. This is IL, this is IR, this is 12 cos omega t plus phi. Okay. He gave minus phi. Actually, in the question, he gave minus phi. It doesn't matter. Okay, now minus phi. Now see, if IL of 0 is 1 ampere and IR of t gave, find phi in degrees. Okay, na? Very interesting question. Chalo, do it 1 minute again. She is asking if IL of 0 is 1 ampere and IR of t is 4 e power minus 3t plus 3 e power minus 4t, what is phase angle phi? Okay, now? Now, sir, what is the meaning of IL of 0? See, IL of 0 means initial current through inductor t equal to 0. And IR of t is an exponential function. So, because here initial condition is given, let us apply KCL at t equal to 0 seconds only. Okay, let us apply KCL at t equal to 0 seconds only. Let us apply KCL at t equal to 0 seconds only. Okay, let us apply KCL at t equal to 0 seconds. So now in that regard, this is clearly 1 ampere. Then at t equal to 0, this becomes 12 cos 0 minus phi. That is 12 cos phi because cos of minus theta is cos theta. And what is IR of 0? E power 0, 1. So this is clearly 7 amperes. Now if you apply KCL, incoming currents equal to outgoing currents. What are incoming currents? 1 plus 12 cos phi is equal to outgoing. So 12 cos phi is equal to 6. Cos phi is half. Phi is 60 degrees. Phi is 60 degrees. Okay, phi is 60 degrees. Okay, that is the answer. Okay, look at very interesting question here. Okay, so now I'm going to another interesting problem here. This is again gate electrical. Very interesting. If power loss in 6 ohms is 0, if power lost in 6 ohm resistance is 0, then find V, voltage V, find voltage V. 20 angle 0 volts, 1 ohm, J1 ohm, 6 ohm, J8 ohm, 5 ohm, 5 ohm. If power lost in 6 ohm resistance is 0, find voltage V. If power lost in 6 ohm resistance is 0, find voltage V. Okay, see the question. If power lost in 6 ohm is 0, then find voltage V. If power lost in 6 ohm is 0, then find voltage V. See, when the power lost in 6 ohm is 0, when current cannot flow. Yes or no? See, power lost in 6 ohm is 0 when current cannot flow. When current cannot flow means, see, with respect to nodal, if suppose this is node voltage V1 and this is node voltage V2 of principal nodes, then power lost in 6 ohm is 0 when current cannot flow. When current cannot flow, these two voltages must be equal. Now, in AC circuits, two voltages equal means equal in magnitude, phase, and frequencies. So, in AC circuits, two voltages equal means, yes, two voltages equal means equal in magnitude, phase, and frequency. So in AC voltage, in AC circuits, two voltages equal means equal in magnitude, phase, and frequency. Okay, no? Equal in magnitude, phase, and also in frequency. Equal in magnitude, phase, and also in frequency. Okay, no? Equal in magnitude, phase, and frequency. Okay, na? So in that regard, yes, equal in magnitude, phase, and frequency. Now, if I do that, yes. Now, first, yes, I treat it like open circuit because current is not flowing. Treat it like open circuit. That means what I will do, the same circuit. Okay, the same circuit, which was like this, because current is not flowing now because voltages are equal in magnitude, phase, and frequency. That is the meaning. So the branch is there, but current is not flowing. So I will treat it like open there. That is the meaning here. Don't confuse with short circuit definition. That is different. So this is 20 angle 0. This is 1 ohm, J1 ohm. This is 5 ohms and 5 ohms. Okay, and this is V is asking. This is V. So these are, yes, V1 and V2 are equal in magnitude. Yes, are equal in magnitude. Yes, V1 and V2 are equal in magnitude, phase, and frequency. So current is not flowing. So current is not flowing means I will treat it as open circuit. Okay, I will treat it as open circuit. Okay, now, chalo, now this is however V1 and this is however V2. Both must be equal. Okay, now V1, V2. Chalo, first let us find V1. Let us find V1. Chalo, if you find V1, V1 is total voltage into same by sum. Same by sum. So V1 will be how much now? 10 root 2 angle 45. 10 root 2 angle 45. That is V1. V1 will be 10 root 2 angle 45. Then what about V2? V2 should be equal to V. No, V2 should be equal to V1. That is nothing but again 10 root 2 angle 45. But if I do voltage division rule, this V2 should be total voltage V into same by sum. Same by sum. Okay, this V2 should be total voltage V into same by sum. From that I can write V is 2V2. So finally V is 2 times, that is 20 root 2 angle 45 volts is the final answer. Is the final answer. Okay, 20 root 2 angle 45. Okay, now. Now this is gate. Wonderful question for electrical. For what supply frequency? For what supply frequency omega? Frequency omega. For what supply frequency omega? The network between A and B. The network between A and B acts like an ideal current source. For what supply frequency omega, the network between AB acts as an ideal current source. Current source are, be careful. This is 1 by 16 Henry. This is 1 farad. Yes, for what supply frequency omega, the network between AB acts as an ideal current source. Okay. For what supply frequency omega, the network between AB acts like an ideal current source. Okay, now for what supply frequency omega, the network between AB acts as an ideal current source. Okay, see for what supply frequency, uh, the network between A and B acts like ideal current source. See what is the property of ideal current source? Yes, in ideal current source, yes, ideal current source internal impedance is infinity. Na ideal current source. See in ideal current source, Z internal is infinity. Yes or no? Infinity. So this Z internal I will equal to infinity. Then it acts like a current source between AB. But what is this? This become plus j omega L. L is 1 by 16 ohms. And what this will become minus j by omega C. C is however 1. So now these two are parallel. So this Z internal will be. Now remove the voltage source because we are reducing the impedance and equating the net impedance to infinity if it is an ideal current source. So now ideal voltage source is exciting this and these are the reactances. Now if it is acting like ideal current source, its internal impedance should be infinity. Na? So now let us find the impedance passive property, remove the source. So this j omega by 16 is in parallel to minus j by omega. So this j omega by 16 is in parallel to minus j by omega. So if you do that, okay, this is this into this. Okay, that is 1 by 16 by sum. By sum. Okay, this is this into this by sum. So now if this has to be infinity, then this has to be 0. Denominator has to be 0. That implies omega by 16 is 1 by omega. So omega square is 16. So omega is 4 radians per second. Answer is 4 radians. That is the answer. Okay, now please understand that. Very interesting. Okay. Then this IES objective question you see. Which is the best theorem to evaluate response in 10 ohm. I'm giving two bits, which is the best theorem to evaluate response in 10 ohm in both cases. Okay, this is network 1. Okay, network 1. This is network 2. Actually, two bits I'm writing together here. First bit is like this. Watch carefully, sir. That observation is important. Which is the best theorem to evaluate response in 10 ohm resistance? Now I'm modifying the same problem. Observe carefully the data, and data has an answer in it. It's just asking, he's not asking to solve by any means because such questions cannot be asked in a GATE and IS. That is why AC steady state calculations are always lengthy, sir. That is why you'll never ask a big problem, but concepts are good. Chalo. Which is the best theorem in each case to evaluate response in 10 ohm resistance? Okay, which is the best theorem in each case to evaluate response in 10 ohm resistance? Everybody, which is the best theorem to evaluate response in 10 ohm resistance? Everybody, which is the best theorem to evaluate response in 10 ohms? See, sir, in both cases, observe. Everybody in both cases, observe. See here, multiple frequency, na, sir, everybody. Here 10 sine 2t, here 10 sine 4t. Here omega is 2, here omega 4, na? Two different frequencies and inductor capacitance. Yes, two different frequency inductor capacitance. What happens, sir? You have to do superposition theorem only. There is no other possibility here. Superposition theorem only. But here same frequency. See right side bit same frequency, but this is in parallel generator form. So millimans. Think sir. Here different frequency only superposition can help us. But right side it is same frequency only Millman's theorem can help us. Okay, only Millman's theorem can help us. Okay, that is the meaning here. That is the meaning. Okay, millimans. Right side millimans because same frequency parallel generator form. Fastest way is millimans. Left side, see Thevenin's is best theorem, but don't see. I won't say Thevenin's is best. Thevenin's is powerful theorem, but it is not best because it takes hell of a time. So best means what? Simple and fast. That is the meaning there. Okay. Left side is superposition. Right side is millimans, not Thevenin's. Gopal, this is not Thevenin's Gopal because Thevenin's is the most powerful theorem, but I don't say it's the best. Thevenin's is very powerful, complex, but millimans is the meaning there. Okay, now we are almost concluding AC steady state. Now this is the last topic, that is power factor correction. Yes, I am giving this question, but we'll take a break of 20 minutes and then we'll continue. So the question is this, that is power factor correction. This topic is power factor correction. Power factor correction. Power factor correction. The question is determine the value of capacitor C, determine the value of capacitor C required, okay, determine the value of capacitor C required to correct, okay, to correct the supply power factor to unity, okay, determine the value of capacitor C required to correct the supply power factor to unity. Now this is the original circuit, sir. Now your supply, yes, your supply is what? Your supply is 220 volt 50 hertz. 220 volt 50 hertz. Okay, and this load is what? 30 at an angle 40 ohms. Okay, 30 at an angle 40 ohms. Okay, now the question is, yes, determine the value of capacitor C, okay, required to correct the supply power factor to 1. We'll continue this after 20 minutes break. Shall everybody take 20 minutes break and we'll continue further. Okay, determine the value of capacitor C required to correct the supply power factor to unity. Yes, everybody. Yes, everybody, please raise your hand. See, if we do hard work for few days, sir, we can. I know evening 5 to 10, 5 to 9 also you have class, right? Yes, everybody. You have class even up to evening, no? Yes or no? I know you have got class even up to evening, 5 to 9. So I will leave you. Okay, in another 1 hour I will leave you. Okay, just 1 hour I will take. Okay, na? Yes. Yes, everybody. Now look at this problem. Now this problem is about finding power factor. Determine the value of capacitor C required to correct the supply power factor to 1. See, this is the meaning. That means why power factor should be 1. You study all these things in power system. But this is a network style problem where I want to find C such that the overall network or supply power factor becomes unity. Now he gave what load here, he gave what type of load. See, he gave impedance in polar form. Generally, we write impedance in rectangular form, but he gave purposefully in polar form. Plus 40. Plus 40, you will get this at something like A plus JB form. A plus JB form means one thing we know. Yes, A plus JB form, one thing we know. This load is inductive. This is lagging power factor load. Lagging power factor load. Yes or no? Now, what is the network style to do? In network analysis or in circuit analysis? In network analysis, okay, in network analysis, what is the style to do? In network analysis, the style is in series natured circuits, okay, in series natured circuits, what we can do, Z is R plus and minus J X net will come. Okay. Now at unity power factor, net impedance is resistance. So what must be 0? If net impedance is resistance, so net reactance must be 0. Net reactance must be 0. Okay, na? Then in parallel natured circuits, net admittance is conductance plus and minus net susceptance. Okay, conductance plus net and minus susceptance. So at unity power factor, net admittance is conductance. Net admittance is conductance. So what is 0? Net susceptance is 0. Net susceptance is 0. So now this is series of parallel nature circuit. Na sir, chalo, I will find total admittance and equate net susceptance to 0. So what I will do now, circuit theory style. So yes, here total admittances in parallel can be added. Now what is the first branch? First branch is capacitor. Admittance is 1 by impedance, now 1 by minus JXC. And this is 1 by admittance. Admittance is 1 by impedance, now 1 by ZL. So this will be, now J operator you take up J, because J is 1 at an angle minus 90. You take up 1 at an angle plus 90. 1 at an angle plus 90 is J only. Na? XC is 1 by omega C. Plus this is impedance. What is the impedance he gave? 30 at an angle 40. 30 at an angle 40. Okay, na? So this will be, okay, this will be like J omega C. Okay, J omega C is, okay, J omega C. Plus this I will write it as 1 by 30 at an angle minus 40 in the numerator. So this is nothing but J omega 2 pi F. F is 50. Okay, he gave that. Okay, F is 50. 2 pi F. Okay, into C. Plus this is 1 by 30. If you convert 1 by 30 angle minus 40, if you convert into, if you convert into rectangular form, okay, you will get this as 0.0255. Okay, minus J point, okay, 0.0214. So now if you further simplify real part and imaginary part, so real part is 0.0255, 0.0255, okay, plus J imaginary part. Now what is the imaginary part? Imaginary part, one is 100 pi C, yes, 100 pi C, minus this is how much? Yes, 0.0214, 0.0214. Okay, now we know that this is the net susceptance. Okay, now we can say, yes, now we can say at unity power factor, we know net susceptance is 0. So if you do that, this 100 pi C is equal to 0.0214. So C is equal to 0.0214 by 100 pi. So if you do that, yes, if you do that, okay, if you do that and simplify, you will get this as, yes, you will get this as 0.78 microfarad. Okay, 0.78 microfarad. Please check it, sir. Okay, if there is any problem. See, one student wrote answer also. I remember one student already wrote the answer here. 68.2. Maybe that is correct, sir. Okay, 68.2. Check it, sir. Okay, I will put a question mark because I need to do, but I did not do. Okay, okay, no problem. No problem. Maybe it could be 0.68 only. Okay, na? Yes, please check it. It could be something like 0.68. I will write your answer only because I did not do that. Okay, chalo 0.68. Check answer. I will write here. Check calculation. I will write like this. Check calculation. Okay, that I'm leaving to you. But answer is this. Answer may be okay. You just take this. Okay. So that is a big observation here, everybody. Yes, everybody should understand this. That in circuit theory, what is the style to do power factor correction? Yes, at unity power factor. Yes, we know at unity power factor, what is the meaning? Net susceptance should be 0 if it is a parallel circuit. So if we equate the net susceptance to 0, I will get this. Okay, na? So with this, I conclude that AC steady state perfectly we completed, sir. Everybody, I want to conclude to say that. Yes, I want to conclude to say that in AC steady state perfectly I completed. Okay, in AC steady state I completed perfectly. In AC steady state, I completed perfectly. Okay, na? Chalo now, sir. Let us expand now. Let us expand. Okay. Now a small topic is coming that is called duals and duality. Okay, duals and duality. Very small topic. Duals and duality. Why I require this, I will tell you now. Okay, with this only, the resonance is easy. Okay, then we can learn other things also very easily. Okay. Yeah, 0.68. Okay, sir. I will consider your answer. Okay. I will consider your answer. Everyone wrote 0.68. Okay, sir. This is the final answer. Okay. I will come because everyone wrote and thank you. Okay, chalo. This is 0.68. Okay, na? Yes. Now I'm going to extension. So AC steady state, every topic, every theorem, everything I covered, sir. Now I'm going to small topic called duals and duality. After learning this, we can start resonance and magnetic circuit because AC steady state is still not over. Because resonance and AC resonance and magnetic circuit is also part of this. That are very big important chapters. And once we complete them, then it is good. Okay, I will take up to 12:30 and then I will take doubts. Okay, now, chalo now, sir. Duals and duality. So first definition: what are duals? What are duals? Okay, two circuits. Listen now. Two circuits are said to be. Yes, two circuits are said to be duals of each other. Okay, duals of each other. Okay, two circuits are said to be duals of each other if mesh equations, yes, if mesh equations that characterize, okay, okay, one of them, okay, mesh equation that characterize one of them. Okay, two circuits are said to be duals of each other if the mesh equations that characterize one of them has the same mathematical form, as the nodal equations, that characterize the other, Okay, two circuits are said to be duals of each other. Yes, if mesh equations that characterize one of them has the same mathematical form as the nodal equations that characterize the other. Okay, so two circuits are said to be duals of each other if the mesh equation that characterize one of them, okay, has the same mathematical form as the nodal equations that characterize the other. Okay, that is the meaning of, yes, duals and duals definition. I will tell you the meaning, sir. Then what is the principle of duality? What is the principle of duality? Okay, what is the principle of duality? Okay, yes, what is the principle of duality? Identical behavior patterns. Okay, identical behavior patterns observed between voltages and currents. Okay, identical behavior patterns observed between voltages and currents of two independent networks demonstrate the principle of duality. Okay. Identical behavior patterns observed between voltages and currents of two independent networks demonstrate the principle of duality. Okay, identical behavior patterns observed between voltages and currents of two independent networks demonstrate the principle of duality. Okay, so let us understand this by taking an example. Okay, now let us understand. Now let me take an example first. Okay, example. Now first I will take series RLC circuit here. Okay, series RLC circuit. Now this is an independent chapter. It could be any function. It could be a DC function or sinusoidal function or any function in time. Okay, this is not like DC or AC. It could be any function in time. Okay, this is some voltage function V of t, which is driving some current I of t. This is R, L, and C. Now passive notation, you know, the direction which current enter is taken as positive. This is VR, this is VL, and this is VC. Okay, here I will write mesh equation. Mesh equation means, of course, KVL. So if I write mesh equations KVL, minus V of t plus VR plus VL plus VC is 0. Okay, then automatically this V of t is VR is IR. Okay, VL is LdI by dt. Of course, these are functions in time. You can write like this: I of t into R. Okay, plus VL 1 by L integral. Sorry, V is LdI by dt. VL is what? Plus LdI by dt. L d by dt of I of t. Now VC is what? VC is 1 by C integral I dt. That is I of t dt. Okay, I of t dt. Okay, that is IR plus LdI by dt plus 1 by C integral I of t dt. Okay, now correspondingly, I am writing the dual. Correspondingly, I will write parallel GCL circuit. Parallel GCL circuit. Okay, parallel GCL circuit. Okay, now here I am taking current source. This is conductance. Okay, this is capacitance. And this is inductance. Okay, so I am writing correspondingly the parallel series become parallel. R becomes G. Okay, this is now current source. I will take now current source I of t. Resistance become conductance. Okay, conductance I will write here. Okay, inductance become capacitance, and capacitance become inductance. Okay, then here source notation. Now this is any time varying function, so this will be something like V of t. Now in passive notation again here, this is positive, this is negative. In this conductance, current should enter positive. Now here I am writing nodal equation. Okay, nodal equation, that is KCL. Okay, KCL. Now if I write that nodal equation at this junction, this is minus I of t, my notation. Okay, plus IG plus IC plus IL is 0. So then what happens? This I of t is equal to Ig, V into G na, that is V of t into G plus IC. Okay, C dV by dt. C d by dt of V of t plus IL. Okay, that is 1 by L integral V of t dt. Okay, now you see this very interesting conclusion. Yes, now the definition you can observe. What is the definition? Yes, two circuits are said to be duals of each other if the mesh equation that characterize one of them has the same mathematical form as the nodal equations that characterize the other. So these two equations are mathematically identical. Mathematically identical. Yes, these two equations are mathematically identical. Hence, they are duals. Okay, that is the definition you see. Yeah, two circuits are said to be duals of each other if the mesh equations that characterize one of them has the same mathematical form as the nodal equations that characterize the other. So because this and this are looking mathematically same, so they are duals. Then what is the principle of duality? Identical behavior patterns. Yes, identical behavior patterns observed between voltages and currents. Okay, identical behavior patterns observed between voltages and currents of two independent networks demonstrate the principle of duality. Okay, identical behavior patterns observed between voltages and currents of two independent networks. Okay, demonstrate the principle of duality. So here how the voltages across passive elements behave, the same way the current through passive elements behave. So identical behavior patterns observed between voltages and currents. Voltages and currents. Yes, identical behavior patterns observed between voltages and currents of two independent networks demonstrate the principle of duality. Okay, na? Demonstrate the principle of duality. Okay, na? That is the meaning there. So now I say these two networks are duals of each other. Now I'm writing the list of dual element. Okay, I'm writing the list of dual element. Okay, yes, some list of, okay, list of dual elements. Dual elements. List of dual elements. Okay, what is the list of dual elements? Yes. Now voltage function, whatever it is dual to current function. Okay, if it is a DC voltage, DC current, so like for example, DC voltage is dual to DC current. Sinusoidal voltage is dual to sinusoidal current. Then you take any function, ramp, step, it is same. Then resistance dual to conductance, capacitance dual to inductance. Okay, then I can say KVL is dual to KCL. Okay, Kirchhoff voltage law, Kirchhoff current law. Series circuit or series nature circuit becomes parallel nature circuit. Parallel nature circuit. Mesh or mesh analysis is dual to nodal or nodal analysis. Okay, nodal or nodal analysis. Okay, then here integral VDT is dual to integral IDT. Okay, then di by dt is dual to dv by dt. That is differentiation of currents is differentiation of voltage. Okay, impedance is dual to admittance. Okay, reactance is dual to susceptance. Open circuit is dual to short circuit. Thevenin's or Thevenin's equivalent is dual to Norton's or Norton's equivalent. Star is dual to delta. Star is dual to delta. Okay, star is dual to delta. Okay, yes, star is dual to delta. If I further continue, yes, pi equivalent is dual to T equivalent. Charge is dual to flux. Charge in conductivity is dual to permeability. Then tree is dual to co-tree. These are all coming in topology. Right now it is not there in the syllabus. Okay, topology old syllabus is not there now. Then tree have twigs. Co-tree have links or cords. Links, we also call them as cords. Then cut set scheduling for trees. We do tie set scheduling for links. Then cut set matrix Q is dual to tie set matrix B. Then initial voltage across capacitor is dual to initial current inductor through inductor. Energy stored in capacitor is dual to energy stored in inductor. Time constant of voltage is dual to time constant of current. Then switch in series getting opened is dual to switch in parallel getting opened. Okay, switch in series getting opened is dual to switch in parallel getting opened. Okay, switch in parallel getting opened. Then if you observe voltage dependent current source like 2Vx is dual to current dependent voltage source 2Ix. Voltage has polarity, and current has direction. Voltage has polarity, current has direction. Okay, so go through this list, I will explain, sir. Okay, go through this list, I will explain. So duals and duality is a small extension, sir. Two circuits are said to be duals. See, slowly so many students are leaving. Okay, so many are leaving. So many are leaving. What to do? Shall we stop? You tell me. Shall we stop? Shall we stop here? I don't know, like why so many left. Just now I told we will do. Sir, I told na sir that hard work now will give you extra time for revision, na sir. See, if we complete early syllabus, na sir, please. So tired, sir. Please stop, sir. No, sir. Please continue. Carry on, sir. Some are telling stop. Some are telling okay. We'll just give introduction to resonance and then I will stop. Okay. Continue. Some are saying continue. Some are saying stop. Okay. Okay. Now listen, everyone. Listen. Okay. We'll continue for another half an hour and stop. 12:30 I will stop. Okay. 12:30 I will stop. 12:30 I will stop. Okay, see now. Okay, see, I gave some list of dual elements. Sir, in this list of dual elements, everybody, I'm continuing up to 12:30. Please cooperate. No one will leave now. No one will leave. Please understand. These are easy, important topics. Only one student is telling stop, stop, stop. Sunil, please. 12:30. I'm going to stop. Majority told to continue. You see now. Now see here. See in this list of dual elements, everybody in this list of dual elements, there are some elements which are originally reciprocal. Now. For example, you see resistance and conductance are reciprocal of each other. Okay. Then impedance and admittance also, and reactance and susceptance also. Okay. Like G is 1 by R, Y is 1 by Z, B is 1 by X. Okay. Please understand. Here, originally speaking, conductance is reciprocal of resistance, admittance is reciprocal of impedance, and susceptance is reciprocal of reactance. Okay. So, but originally they are reciprocal, but this is different concept of duality. Here, dual relation. Here, dual relation is different. Here, dual relation is different. Dual relation is different to original reciprocal relationship. I will ask a meaning there. Okay, here also you see, sir, this comes from graph theory. Okay, this comes from transients. Okay, this comes from transients. Now I'll ask a question here. Okay, question is what is the dual of okay 3 ohm resistance? Shall everybody write the answer? What is the dual of 3 ohm resistance? Okay, what is the dual of 3 ohm resistance? Okay, please understand. What is the dual of 3 ohms? Answer is simple. 3 Siemens only. 3 Siemens only. Don't say 1 by 3 Siemens. See, originally 3 ohms is 1 by 3 Siemens. But here dual of 3 ohms is 3 Siemens. Another question. Another question. What is the dual of? What is the dual of? Okay. 4 plus J3 ohms. Chalo, I don't want to give any hint. What is the dual of? Okay, 4 plus J3 ohm. What is the dual of 4 plus J3 ohm? What is the dual of 4 plus J3 ohm? What is the dual of 4 plus J3 ohm? Okay, na? Yes, answer is simple. Yes, 4 plus J3 Siemens. It is impedance, na? So it is impedance. It is 4 plus J3 Siemens. That's it. That's it. What all students wrote? Let me see. The students who wrote 1 by 3 are wrong, sir. The first dual of 3 ohms is 3 Siemens only. Okay, na? And dual of this 4 plus J3 Siemens only. Very good. Because you see, this is actually impedance. Na? Ohms means impedance. That is 4 plus J3. What does it indicate? It is like resistor in series with inductive reactance. Like that I can model na resistance in series with inductive reactance. So what is the dual of this? See here, admittance. Admittance is 4 plus J3. Admittances in parallel can be added. So admittances in parallel can be added. So automatically here 4 Siemens and positive susceptance is capacitive. Positive susceptance is capacitive. Okay. Here positive reactance is inductive. Here positive capacitor, positive susceptance is capacitive. So series RL become parallel GC. Series RL become parallel GC like that. That is a concept there. Okay. That is a concept. Okay. I'm writing this question. Construct. Okay. Construct. Let me write correct spelling. Construct the dual of the following circuit. Okay, construct the dual of the following circuit and verify by writing corresponding corresponding mesh and nodal equations. Construct the dual of the following circuit and verify by writing corresponding mesh and nodal equations. Okay, na? Okay, construct the dual of the following circuit and verify by writing corresponding mesh and nodal equations. I will give in the next page, sir. Yes. V of t R L C G R L C G. Okay, chalo. I want the dual. Everyone listen now. I am writing the answer. See now. See, first of all, meshes become nodes. How many meshes are there? This is mesh 1, node 1. This is mesh 2, node 2. And mesh 3, node 3. And I will take reference also. So this is mesh 1, node 1, mesh 2, node 2, and mesh 3, node 3, and reference also. So I'm writing the same thing right side here. See, this becomes node 1. This becomes node 2. This becomes node 3. Okay, and this is the reference. Okay, and this is the reference. Now, sir, now what I'm trying to do, okay. So now what I can do, yes. Now, first include the external branches of each mesh. See in this first mesh, this is the external branch now. So in the first mesh, the external branch is this voltage source only. This resistance is common branch, this inductor is common branch. So in the first mesh, this voltage is the common branch. So there is a voltage between, yes, node 1 to node 0. Correspondingly, it becomes what? Current source between 1 and 0. It becomes current source. That V of t become I of t. V of t become I of t. And here in the second mesh also, yes, there is a current source between node 2 to 0. So this becomes a voltage source. This becomes a voltage source. This is V of t. V of t. Okay. Then between 1 and 2 there is inductance. Polarity direction I will tell you wait sir. Between 1 and 2 there is inductance. So automatically this is between 1 and 2 become capacitance. 1 and 2 this becomes capacitor. Then this capacitor is between 2 and 3. 2 and 3 capacitor becomes 2 and 3 inductor. 2 and 3 inductor. Then between 1 and 3 resistor become, yes, 1 and 3 inductance. And finally between 3 and 0, because external branches are refer to reference node. All external branches of mesh, you better refer with reference node. What are the external branches? Like in first mesh, voltage source is external branch, so refer with reference node and write it 12. In second mesh also, current source is external branch, refer with reference node and write 12. And in third mesh also, conductance is external branch and refer with 12. But here 3 to 0 there is a conductance, so 3 to 0 becomes resistance. Now polarities directions are polarity directions are only notations are like here you see in mesh equation I write KVL clockwise now. In mesh equation I write KVL clockwise. When I write KVL clockwise, yes, when I write KVL clockwise, I write minus V of t now. I get minus V of t. So correspondingly here also in nodal I should get minus V of t. But according to me in nodal, my notation is current leaving I take positive, but current entering I will take negative. So that is why same negative should come. Because here clockwise minus V of t voltage, here KCL minus I of t current. Here clockwise minus V of t voltage, here current minus I of t. Okay, that is the meaning. Okay, that is the meaning there. There is a meaning. Here clockwise KVL minus V of t, there here minus I of t. Okay, here clockwise minus V of t, there current minus I of t. Okay, that is the meaning there. Okay, similarly here in second mesh I2, if I write second mesh equation, I2 is minus I of t. Okay, I2 is minus I of t, there V2 should be minus V of t. V2 should be minus V of t. So I2 is minus I of t, should be V2 minus V of t. Okay, this I2 is minus I of t, should be V2 minus V of t. Okay, that is the meaning. Now let us check them by writing the equations. Suppose you write mesh equations here. Shall everybody look at the mesh equation? Minus V of t clockwise, okay, plus R into, that is I1 minus I3 plus L. Voltage across inductor na, that is L into dI1 by dt minus dI2 by dt equal to 0. That is first equation. Correspondingly, if I write nodal here, yes, corresponding if I write nodal here, this is minus I of t, yes, plus this is G into conductance V1 minus V3, but what about the current in capacitor C dV by dt na? Yes, that is C into, I can write here dV1 by dt minus dV2 by dt equal to 0. Now you see, sir, this first equation and first A equation both are same, na? First equation and first A equation both are same. Yes. Similarly, if I go to the second equation, mesh 2, I2 is minus I of t. Simple. I2 is minus I of t. Here V2 is minus V of t. Then third, if I go to the third mesh equation, V is I by G. That is I3 by G. Okay. Plus here voltage. 1 by C integral. 1 by C integral. Okay. I3 minus I2 dt. C dV by dt. That is R into. Okay. I3 minus I1 equal to 0. Okay. Okay, na? So correspondingly, if I write nodal equation here, it is V3 by R, V3 by R, okay, plus this is 1 by L integral, okay, V3 minus V2 dt, okay, plus this is G into V3 minus V1 equal to 0. That is equation 3a. Equation. Okay, you see both are similar or not? Okay, you can ask doubts now. We will close, but today you ask doubts. We'll do extra things and start resonance tomorrow. Okay, tomorrow will be big day. Yes, tomorrow will be a big day for AC steady state as resonance and magnetic circuits will conclude. Okay, chalo now. Yes, Sangeeta, what is your doubt?
Sir, how the 3 Siemens will come, sir, in previous questions?
Understand, originally G is 1 by R.
Okay.
But this is not the meaning. Dual relation is just a dual of 3 is 3 Siemens only. That is why R becoming G means 5 ohms becomes 3 Siemens. That's it. 5 ohms become 5 Siemens like that. But originally, that is what I'm trying to say. Original is different to this chapter. Originally, G is 1 by R.
Okay.
But this chapter is dual modeling of the resistance is like 2 ohms become 2 Siemens, 5 ohms become 5 Siemens. That is why I proved mathematically here. See, here also you see now. Even in this problem also you see. For example, in this problem also you see. Here R is there, G is there, na?
Yes, sir.
The corresponding equations became same, na? Mathematical equations became same, na?
Yes, sir.
That is the reason we take like that. So this chapter is not the meaning of original relation. This chapter is a dual relation. That is why dual of 3 ohms is 3 Siemens and dual of 4 plus J3 is 4 plus J3 Siemens only. But generally you may say, sir, why can't I write this Y as 1 by Z? That is different meaning. That is not duality chapter. That is original chapter. Originally Y is 1 by Z. But in this chapter, we need not follow. This is only mathematical relation chapter, but not the original relation.
Yes, sir. Got it, sir. Thank you, sir.
Okay, right. Next, Vishnu.
Sir, my doubt is regarding the last one only, sir. That last network, how did we consider the directions of the...
See, everybody listen. See, one student is asking how to consider direction and polarity. See, direction and polarity is whatever notation you follow. It need not be even the same what I took. Only thing you have to check is whatever way you write directions and polarity, your max equations you should be same. Like left side mesh equations, right side nodal equations are ditto same, including polarities and directions. Like you see, what is my notation? See, left side mesh analysis I compare, right side nodal analysis I compare. In left side mesh analysis, first mesh equation when I write clockwise KVL, I get minus V of t volts now.
Oh.
So in nodal also, what is my notation? Current leaving the node I take positive, but current entering the node I take negative na.
Oh.
So here minus V of t k means there also minus I of t should come. But what is minus I of t means entering the node.
Okay.
Like that I have to take. See the second equation. Here I2 is minus I of t, second KVL, it is a link equation, I2 is minus I of t. So there also V2 should be minus V of t with respect to reference. That is why minus I took default.
Okay, so how the how with respect to that person, how he is writing KVL and KCL depending on that.
Very good, correct. With any style of writing, any notation, how you are getting plus and minus correspondingly managed there. Only equations must be balanced.
Okay, sir. And one more thing is this dual network. For instance, what my understanding is this dual network not intended to like solve. I mean, if you're finding difficulty in solving this network, if you consider dual and then solve it, so will it become easier? Or
best application is analogous systems in controls.
Analogous system.
Spring mass damper system.
Yes sir, yes sir.
That is because of this chapter only it came.
Yes sir.
That is why mathematical modeling of mechanical system is very difficult, but we model them into electric circuits as dual networks and do na. That is why solution to a robot you will get with circuit analysis.
Okay, sir.
That is the meaning. Understood?
So this is more like modeling this.
Mathematical modeling chapter. Mathematical modeling chapter. Here we are not interested in answer also. We want to model it into dual and do the solution faster and understand the physical systems.
Okay, sir.
Okay?
Yes, sir. Thank you, sir.
Yes. Bimilendu Swine.
Yes, sir.
Tell me.
Sir, doubt in a maximum power.
Tell me, what is your doubt?
Here, that two problem we are considered that one is capacitor is changing, so that XC is equals to minus of XL.
Okay.
In this case, if I am substituting that J100 ohm,
Which one? Can you tell me the problem specifically?
yes, sir, that problem will be next, sir, J8. That before that inductor capacitor combinedly that only capacitance vary.
This one, huh?
J100, yes, yes, sir. In that problem, let's suppose. Yes,
Ah,
sir. Here I am varying that XL.
ah,
If any question it is given that 4 options are there.
ah.
If it will be say that I am varying that XC, such that and XS also varying.
You are wearing XL also, na?
XL means any case is there possibility that XL should be 0 such that maximum power will be transferred to the load.
No. If load, if it is a pure DC load or the reactance of the system. See, like for example, this concept is linking there. See, in this case, what is it? He kept both L and C in the load side only, na?
Yes, sir.
The source side is only resistance, na?
Yes, sir.
So that is why what is the logic? The load should be such that the net reactance should be 0.
Yes, sir.
Same concept.
Sir, I have means that if that inductor is replaced with some capacitor.
Compensating element for
And both capacitor are vary, then that load means that 5 millihenry is in the source side.
Both what you are wearing, both?
Both means inductor is replaced with capacitor and load is also capacitor, means 2 capacitors are there.
Then we cannot do. It comes under the only thing. See, if both are capacitor, then there is no concept of compensation.
Means,
Real power is not maximum. Whatever maximum you can get, that is the only thing. Because if you have compensating element, if it is a source inductor, put load side capacitor. Or if source is capacitor, put load side inductor.
Okay, means I am saying that if both are capacitor, then if capacitance is such that reactance will be 0, then can I get maximum power?
That is the only option. Suppose your imagination is if this is also capacitor, this is also capacitor, then don't connect it. That is the only option. Source side you cannot design anything. So load side you remove the reactance. That's it.
Sir, in that next question, sir. Here, when capacitance and I am writing that total equation, that resistance and reactance in the term of capacitance. Then that real part is also depend on the capacitor only.
No, here it is indirectly the design will be such that indirectly the mathematics will tell. Suppose you substitute even the real part. See, you put this real part also will come same automatically. You see, what is the answer we got? We got C as 10 millifarad, na? You substitute, answer will come same. Suppose here also you see 1 by omega square, that is 100 square, 100 into 100. Okay, C square. C is how much? 10 milli square. Okay, this is also 10 square, 100 into milli. Milli become micro, micro plus 1. So this is 1 plus 1, 2. 1 by 2 is again 0.5 only, na?
Okay.
0.5 is automatically coming there.
Means sir, here also we can use that is RL is equals to RS square plus XL plus XS square. That will be under.
The indirect requirement here is we are managing C such that the net reactance is 0. Okay. Yeah, that is the meaning. Okay. Sweta.
Hello, sir. Sir, could you please once open the list of dual elements?
I will open. Tell me what is your doubt.
Sir, ट्री से ऊपर क्या बना हुआ है वो?
वो कंडक्टिविटी परमिएबिलिटी ये सिग्मा है इसको कंडक्टिविटी बोलते हैं और ये न्यू इज परमिएबिलिटी. इलेक्ट्रिकल कंडक्टिविटी इज इक्वल टू मैग्नेटिक परमिएबिलिटी.
ओके सर, बाकी डाउट कवर हो गए अभी.
राइट, वेरी गुड. शिवा
sir, in special case C, sir.
Tell me what is your doubt.
Sir, there we are bearing the load, the reactance of the loads, the reactance on the load side, and how you told that the magnitudes are fixed?
Because resistances are constant. After net reactance becomes 0, resistances are uncontrolled. You are not controlling resistance, so different resistance will make different magnitudes.
No, sir, but by varying the reactance value, we can match the impedance values. So is it possible, sir?
No, the condition itself we are applying. What is the condition? We adjust such that the net reactance becomes 0.
Okay,
So
sir.
net reactance 0 means phase angle is not there. So phase balancing is done.
Yes, sir. Sir, I have the same thing, one more, sir. So if we like vary the reactance value, uh, the impedance angle will vary, right, sir?
Hmm.
Okay,
We
sir.
are
So,
varying such that the net reactance is 0. That is what after application only we are talking. We are varying such that the net reactance is 0. So automatically when XL is minus XS, magnitudes are same we are telling, but RL is not equal to RS now.
okay, sir.
That is the reason. That is the reason we cannot get it. So magnitudes can never match because resistances are fixed here.
Okay, sir.
Okay.
Sir, then the next problem, sir.
Tell me.
Be in the next slide. Sir, I don't get this problem.
Here in source side, what we have to vary. First of all, if you can vary the source side, which is already designed, make net reactance 0. Again, XS should be minus XL. Then unity power factor become. Then it becomes pure resistor problem. And now in pure resistor, we know minimum resistance in the source will give maximum power in the load. We learned in DC's concept, na?
Yes, sir.
So first of all, XS should be minus XL. Then only net reactance becomes 0. And what about resistance? Minimum resistance. So reactance should be such that it should compensate, and resistance should be such that it should be minimum. In power system, this is called reactive power compensation, and this is minimization of losses in power system.
Sir, here, like in while applying the maximum power transfer theorem, the load side reactance should be varied. Is it so, sir? Or we can like vary any source resistance?
That is why this all cases came na. In books they don't discuss all these things, but in GATE and IES they are asking. There are so many possible cases. Actually, both can be varied. Both you can vary. You can put a capacitor bank. Like in our machines lab, we have inductor bank and capacitor bank also we vary na.
Yes, sir.
That is an expensive process, so we don't do. But you can do. Practically, you can do. That is why in network theory all are possible cases.
Okay, so because in case of DC, we are varying only the load side resistance, so that's right.
DC inductor capacitor we assume not to be working, but in AC everything works, and in that all possible cases we are studying.
Okay.
Okay.
And then in case of duals, like last one, 4 plus J3.
What is your idea? What is your doubt?
No, sir. I just want to conclude whether you tell me whether it is right or not. So here we are modeling the same series network into parallel, so that's why we are getting the same the conductance and the.
This is only a mathematical modeling chapter. Here answers are not important. So writing a dual is only a mathematical model to get same mathematical equations. Okay, and later solution will tell the behavior aspects of this. That is what definition we told now. Yeah, duality. What is the principle of duality? Identical behavior patterns. So here we are modeling such that yes, the mathematical equations are same.
Okay.
Okay,
so if the same series network is modeled like instead of going for parallel, if the same series network is modeled, then we'll be getting 1/4 and 1/J3.
Yes, correct. Tomorrow I will do with numericals also tomorrow. Okay.
Yes, sir.
Okay. Okay. Then Imtiaz.
Good afternoon, sir.
Tell me, Imtiaz.
Sir, that problem is clear, sir. Means
Good.
special case, say after that first problem.
Yes, you got that clarity?
Hi, sir. Yes, sir, I got. But what I did means, I use that the maximum power theorem principle, sir, as Vs equal to V/2 at the load.
Okay.
With that, I got means RL plus, XL/2, sir.
Okay.
Is it right?
Where this problem only?
First problem, sir.
This problem,
Before that, sir. First problem today's means. Next. Sir, before this one, sir. Sir, could you assess the maximum power 50% of the power is come means Vs/2 at the load side?
In this case, ideally, no. In this case, we cannot. In this case, what happens now? We are adjusting the source to maximize power in the load. This is different. In this case, we are adjusting the source to maximize power in the load. then net reactance should be 0 and resistance is 0. So here we cannot argue that 50% drop will occur.
Means it's only applicable for the DC also.
Because in practical case, load is a variable, for source is fixed.
Yes, sir.
That is the reason we cannot argue that here.
Okay, sir. Because first I got from that we RL by 2, that's XL by 2, sir.
Yes, correct.
Sir, one more, sir. In the all three cases, which one is practical? Means both we can variable, no, sir, RL and XL.
Both variable is also not practical because varying reactance is exclusively costly. So the most practical case is for pure resistor. This is the case. That is case B. Yes, case A and case B are more practical. Case B and case A only. Case A, if load is resistor like heater, incandescent bulb, that is the best case. And case B, where only resistance is there. That means in both cases, resistance variable is only practical. Because reactance we can do, but it is expensive, very costly. And compensating source reactance is not possible. Like in power system, you know, source reactance is so large that as a customer, I cannot do compensation for the entire source now.
Yes, sir.
Like that. It is not possible practically. Theoretically, we can talk, but practically not possible like that.
Okay, sir.
Okay?
Yes, sir, I got it.
Okay,
Thank
so
you, sir.
tomorrow everybody again 7 to 12:31 we will go. Let us see. By the mood I will change. So tomorrow
Hello,
again
sir.
we will meet. Tell me Sweta.
Sir, can I ask one more question?
Tell me.
सर वो जो एक सर्किट था जिसमें A से B पावर ट्रांसफर करनी थी सर, जैसे अभी इन्होंने पूछा
बोलो
सर,
what is it about?
उसमें मतलब R को 0 क्यों नहीं ले सकते? जैसे मतलब जैसे सीरीज में R होता है तब बोल
simple explanation. Load side itself is maximum power, which for real power consumption. ना real power consumption तो R तो रहना पड़ेगा.
ओके सर.
अगर R 0 किया तो we are not absorbing any real power which is utilizable part.
ओके सर.
Okay?
यस सर. अगर मतलब इसमें आगे और रेजिस्टर्स लगे होते
then इसका कम करो, then you will get more.
ओके सर.
Okay?
यस सर, थैंक यू सर.
Right. So everybody, we will meet tomorrow again 7 o'clock.